For 75 million years, the colossal dinosaurs ruled Earth, their reign ending abruptly in a catastrophic event that forever altered the planet's biological trajectory. In the wake of this mass extinction, the Earth did not become a desolate wasteland. Rather, it blossomed into a fertile cradle of evolution and adaptation. This new era heralded the ascendancy of mammals, setting the stage for the eventual emergence of humans. Join us as we delve into what really happened after the dinosaurs went extinct. The extinction of the dinosaurs, which occurred about 66 million years ago, is a captivating area of study in paleontology and cosmology. The leading event believed to have triggered this mass extinction was a colossal asteroid impact. Scientists point to a site in the Yucatan Peninsula in Mexico called the Chicxulub crater, which is around 180 kilometers wide and believed to have resulted from a 10-kilometer wide asteroid. The impact would have released immense amounts of energy, equivalent to billions of atomic bombs, generating widespread wildfires, tsunamis, and releasing dust and debris into the atmosphere. This debris would have significantly blocked sunlight, disrupting photosynthesis and leading to a cascade of ecological failures. In addition to the asteroid impact, another substantial factor was volcanic activity, particularly in what is now the Deccan Traps in India. This volcanic region experienced large eruptions that released vast amounts of lava, ash, and gases over thousands of years. The gases, particularly sulfur dioxide and carbon dioxide, would have contributed to climate change, leading to global cooling and acid rain, further destabilizing ecosystems that were already struggling. Together, these catastrophic events created harsh conditions for life on Earth. The darkness caused by the debris cloud, along with the harsh chemicals in the atmosphere from the volcanic eruptions, could have led to the extinction of many plant species, forcing herbivorous dinosaurs to die out from food scarcity. This, in turn, disrupted the food chain, leading to the decline of carnivorous dinosaurs that depended on them. The combination of these factors created a perfect storm of destruction that marked the end of the Mesozoic era. This event did not just mean the end for dinosaurs. It allowed for the rise of mammals, eventually paving the way for the evolution of humans. Reflecting on this significant moment in Earth's history helps us understand the fragility of life and how the planet's systems are inextricably linked to cosmic events beyond our control. Scientists have pieced together the timeline of dinosaur extinction through multiple lines of evidence, primarily focused on geology, paleontology, and radiometric dating. The cataclysmic event believed to have caused this mass extinction occurred around 66 million years ago. This is when the last of the dinosaurs vanished from the Earth, a shocking end to a reign that had lasted approximately 165 million years. One of the most pivotal pieces of evidence comes from the study of sediment layers. These layers, often found in what are known as the Cretaceous-Paleogene boundary, contain a distinctive layer of iridium, a metal that is rare on Earth's surface but more common in asteroids. This discovery suggests that a massive asteroid impact, likely the one that struck the area now known as the Yucatan Peninsula in Mexico, played a crucial role in the extinction event. By meticulously dating the sediment layers above and below this threshold, scientists can establish a timeline that correlates with the fossil record of dinosaur species. Another important component is the analysis of fossils themselves. Paleontologists examine the chronological appearance and disappearance of various species across different locations. By correlating these fossil findings with the dating of rock layers, scientists can outline a clearer picture of the ecological landscape during that time. Notably, the disappearance of large dinosaur species coincides with immediate changes in climate and habitat alteration, further indicating the timing of extinction events. Finally, advances in radiometric dating techniques allow for more precise measurements of the ages of rocks and fossils. This scientific method utilizes the decay of radioactive isotopes to determine the age of materials. By combining this data with the geological and fossil records, scientists have created a well-supported timeline that gives us insight into how and when dinosaurs went extinct. Each discovery sheds light on the past, allowing us to understand the complex processes that led to one of the most significant events in Earth's history. The asteroid impact theory proposes that a colossal asteroid struck Earth around 66 million years ago, leading to the dramatic extinction of approximately 75% of all species, including the dinosaurs. One of the most compelling pieces of evidence supporting this theory is the discovery of a layer of sediment known as the Cretaceous-Paleogene boundary. This layer is rich in iridium, a metal that is rare in Earth's crust but commonly found in asteroids. The anomaly of iridium levels in this boundary layer has drawn significant attention and sparked scientific inquiry. Further investigations have led scientists to the Yucatan Peninsula in Mexico, where they found the Chicxulub crater. This massive impact site, measuring about 180 kilometers in diameter, perfectly aligns with the timing of the extinction event. Geological studies of the crater reveal evidence of shock waves and thermal effects caused by a significant impact, lending substantial credence to the theory. The size and nature of the crater suggest that the impactor was roughly 10 kilometers in diameter, creating catastrophic consequences not only locally but globally. In addition to the iridium layer and the Chicxulub crater, numerous studies have documented the aftermath of the impact. Fossil evidence indicates a rapid decline in biodiversity following the event, with many species showing signs of environmental stress. Isotope analysis found a shift in carbon ratios in ocean sediments, indicating a major disruption in the carbon cycle, likely due to dust and debris blocking sunlight, which led to a collapse of ecosystems. Lastly, computer simulations and models of the impact provide further insights. These models predict drastic climate changes, including prolonged darkness and a dramatic drop in temperatures, which would have been catastrophic for many life forms. Together, these strands of evidence weave a robust narrative supporting the asteroid impact theory, painting a picture of a pivotal moment in Earth's history that reshaped the trajectory of life on our planet. Volcanic activity has played a pivotal role in several extinction events throughout Earth's history, notably during the Permian-Triassic extinction, often referred to as the Great Dying. About 250 million years ago, vast volcanic eruptions released enormous quantities of lava in what is now Siberia. This immense volcanic activity led to the creation of the Siberian Traps, a region characterized by extensive basalt formations. The eruptions themselves were catastrophic, but the real danger lay in the gases they emitted. As the volcanoes erupted, they spewed out carbon dioxide and sulfur dioxide in massive amounts. These gases led to dramatic shifts in the atmosphere and climate. Increased carbon dioxide levels fostered a greenhouse effect, which resulted in global warming. This heating altered ecosystems and habitats, pushing many species to their limits. Concurrently, sulfur dioxide generated acid rain, drastically affecting water sources and soil health, creating a highly toxic environment for both plant and animal life. The consequences of these climatic changes were dire. Ocean temperatures rose and the acidity of the waters increased, leading to significant disruptions in marine life. Marine ecosystems that thrived on stable conditions began to collapse. Species that could not adapt quickly to these fast-changing environments faced extinction. It's estimated that up to 95% of marine species and 75% of terrestrial vertebrates vanished in this catastrophic event. Volcanic activity catalyzed one of the most significant extinction events by creating an environment that was hostile to life as it was known. The interplay of climate change, ocean acidification, and habitat destruction illustrates how powerful geological processes can reshape the course of life on Earth. The after-effects of these eruptions resonate through time, reminding us of the delicate balance that sustains our planet's biosphere. The extinction of the dinosaurs about 66 million years ago brought about remarkable shifts in the Earth's environment. Before their demise, dinosaurs roamed a world rich in plants and diverse ecosystems. However, the catastrophic event, likely triggered by a massive asteroid impact, led to the rapid disappearance of these ancient reptiles. This event had far-reaching consequences that forever altered the planet's landscapes and climates. In the aftermath of the extinction, the immediate changes included a decline in plant diversity. Some species struggled to survive in the altered conditions as sunlight became scarce due to dust and debris propelled into the atmosphere. This lack of light hindered photosynthesis, leading to a collapse in the food chain that supported herbivorous dinosaurs and, in turn, the carnivores that preyed on them. As a result, many ecosystems suffered, giving rise to barren landscapes that were drastically different from the lush habitats of the prehistoric era. As the dust settled and conditions began to stabilize over thousands of years, the environment slowly started to recover. Flora began to recolonize the ravaged landscapes, with ferns and flowering plants making a comeback. This renaissance of plant life was crucial, as it set the stage for the evolution of new ecosystems. The periods that followed saw the emergence of mammal-dominated biomes, reshaping the structure of life on Earth. These new ecosystems fostered a rich biodiversity, paving the way for the mammals to evolve and thrive in new ecological niches. The extinction of dinosaurs ultimately opened up vast opportunities for other species, leading to the emergence of modern mammals, birds, and even flowering plants. It allows us to appreciate the delicate balance of life and how catastrophic events can reshape the environment, leading to new beginnings. This historical moment significantly altered the trajectory of life on our planet, demonstrating the resilience of nature and the ever-changing tapestry of Earth's biosphere. The extinction of the dinosaurs, approximately 66 million years ago, is one of the most significant events in Earth's history. This mass extinction is thought to have been triggered by a combination of catastrophic events, including a massive asteroid impact in what is now the Yucatan Peninsula in Mexico and extensive volcanic activity in present-day India. While these events spelled disaster for many species, including the colossal dinosaurs, mammals managed to find a way to survive and eventually thrive. Mammals, which were relatively small and largely nocturnal during the age of dinosaurs, had several advantages that aided their survival. Their size allowed them to escape the immediate dangers posed by catastrophic environmental changes. As the dinosaurs vanished, the world transformed dramatically, with temperatures plummeting and sunlight obscured for an extended period. This created a realm that was harsh for larger animals, but, for the smaller and more adaptable mammals, offered new niches to exploit. Those that could burrow or seek shelter had a better chance of surviving the harsh conditions brought on by the aftermath of these cataclysmic events. Moreover, mammals had a diverse diet, which gave them an extra edge. While many large herbivores depended on specific vegetation, mammals could consume a wide range of foods. This adaptability helped them secure food sources when ecosystems were thrown into disarray. In the years that followed the extinction of the dinosaurs, mammals began to diversify rapidly, filling ecological gaps left behind. They evolved into all the various forms we recognize today, from the tiny mouse to the massive whale. The extinction of the dinosaurs opened a door for mammals. As these small, resilient creatures weathered the storms of changing climates and resources, they laid the groundwork for a new era in biological history. From their modest beginnings, they would rise to dominate the planet, eventually giving rise to humans and countless other species, proving that in the face of extinction, adaptability and resilience could foster new life. After the dinosaurs vanished around 66 million years ago, the world underwent a dramatic transformation. The extinction event, likely caused by a massive asteroid impact, wiped out nearly 75% of all species. As the dust settled and the sun began to shine again, a new era unfolded for mammals, which had been small and somewhat insignificant during the reign of the dinosaurs. The earliest mammals following this cataclysmic event were primarily small, shrew-like creatures. They were mostly nocturnal, taking advantage of the cover of night to evade larger predators. These mammals were likely insectivorous, feeding on insects and other small invertebrates. Their size could be likened to modern-day rodents. These adaptations allowed them to thrive in an environment that had drastically changed, filled with new opportunities but also new challenges. With the dinosaurs gone, mammals began to explore and occupy ecological niches that had once been dominated by these reptiles. With the dinosaurs gone, mammals began to explore and occupy ecological niches that had once been dominated by these reptiles. As forests regrew and ecosystems diversified, mammals started evolving more significant traits. Some mammal lineages would eventually see dramatic increases in size, leading to the emergence of larger herbivorous and carnivorous species in the millions of years to come. Remarkably, this pivotal moment in Earth's history set the stage for mammals to become the dominant land animals. Over time, they would evolve into a vast array of forms, including the remarkable creatures we know today, such as elephants, whales, and primates. Each adaptation and evolution builds upon this fundamental shift when the mammals first began to flourish in an empty playground, free from the dominance of the dinosaurs. The end of the dinosaurs, which occurred around 66 million years ago, is one of the most significant turning points in Earth's history. This mass extinction event, marked by the dramatic impact of a large asteroid and widespread volcanic activity, led to the disappearance of approximately 75% of Earth's species, including the formidable dinosaurs that had dominated the planet for millions of years. The abrupt void left by these giant reptiles set the stage for a remarkable transformation in life on Earth. With the dinosaurs gone, the ecological landscapes changed drastically. Their extinction allowed many smaller creatures, including the early mammals, to venture into newly available habitats unopposed. Prior to this event, mammals were largely small, nocturnal creatures, often restricted to niches that the dinosaurs had not exploited. If you picture this vast, open world with fewer massive predators, it becomes clear that opportunities for survival and diversification were ripe for those smaller mammals. In the wake of the dinosaurs' disappearance, mammals underwent an incredible adaptive radiation. This term refers to the rapid evolution of numerous species from a common ancestor, filling diverse roles in the ecosystem. Some mammals evolved to take advantage of new food sources, while others developed various adaptations to their environments. Over millions of years, this led to the emergence of a wide array of forms, from the tiny shrew-like creatures to the towering mammals that roamed the plains. Ultimately, the extinction of the dinosaurs did not just create a chance for survival, it opened the door for mammals to thrive, innovate, and diversify in ways that would lead to the development of modern species. From these humble beginnings, mammals evolved into the dominant land animals, culminating in the rise of primates and eventually humans. The end of the dinosaurs was, in many ways, just the beginning for mammals, setting off a chain of evolutionary events that would forever alter the course of life on our planet. Climate change has played a pivotal role in shaping the evolution and diversification of mammals throughout Earth's history. One of the most significant periods was during the late Mesozoic era, when major shifts in climate were linked to the gradual decline of the dinosaurs. As the climate began to cool, different habitats emerged, paving the way for mammals to adapt and thrive in niches that were previously unavailable to them. This period set the stage for an explosion of mammalian diversity. As we moved into the Cenozoic era, which began around 66 million years ago, the aftermath of the mass extinction event that wiped out the dinosaurs led to dramatic changes in the Earth's climate. The warming trend that followed created new environments, from lush forests to expansive grasslands. Mammals, which were largely small and nocturnal during the time of the dinosaurs, began to evolve into a wide variety of forms and sizes. Species adapted to these new environments filled ecological roles left vacant by the extinct reptiles. Additionally, changes in climate influenced migration patterns and the development of distinct mammalian groups. For example, the cooling and drying conditions during the late Cenozoic led to the expansion of grasslands, which favored the evolution of large herbivores like elephants and horses. These animals adapted to graze in open spaces, while carnivores evolved to hunt them. The cooling climate also contributed to the emergence of ice ages, further driving diversification as species adapted to survive in colder environments. In conclusion, climate changes have been a fundamental force in the evolutionary story of mammals. By continually reshaping habitats and influencing survival strategies, changes in temperature and precipitation fostered the incredible diversity of life we see today. From the tiny, fur-covered creatures of the Mesozoic to the majestic mammals that roam our world now, climate dynamics have carved the path of mammalian evolution, illustrating the intricate relationship between life and its environment. Early mammals emerged at a time when the Earth was a very different place, having just survived a mass extinction event that wiped out the dinosaurs around 66 million years ago. This transition opened the door for mammals to evolve and thrive in new ecological niches. Among the most significant adaptations that early mammals developed were changes in their body temperatures, reproductive strategies, and sensory capabilities. One of the key adaptations was the development of warm-bloodedness, or endothermy. Unlike reptiles, early mammals could regulate their body temperature internally, allowing them to inhabit a wider range of environments, from the hot deserts to the cold forests. This ability to maintain a constant body temperature offered them a significant survival advantage, especially during times of climate fluctuation. It enabled them to remain active and forage for food, even when conditions were less than ideal. Another notable adaptation was the evolution of fur, which provided insulation against temperature extremes. Fur not only helped with thermoregulation, but also played a crucial role in camouflage, giving mammals a tactical edge in avoiding predators. Additionally, early mammals began developing more complex teeth, allowing for a varied diet. Differentiated teeth, including incisors for cutting, canines for tearing, and molars for grinding, gave them the versatility to exploit different food sources, from fruits to insects. Moreover, early mammals exhibited remarkable advancements in sensory perception. As nocturnal creatures, many evolved acute senses of hearing and smell, which were critical for finding food and avoiding dangers in the dark. The development of the middle ear and specialized bones allowed for better sound transmission, making these early mammals adept at detecting predators or prey. These adaptations laid the foundation for the diverse array of mammalian life we see today, showcasing the incredible resilience and innovation of these early creatures. The connection between dinosaurs and birds is one of the most remarkable stories in the history of evolution. About 150 million years ago, during the late Jurassic period, certain dinosaur species began to develop features that would eventually lead to the emergence of birds. The most notable of these were theropods, a group of bipedal carnivorous dinosaurs that included the fearsome Tyrannosaurus rex and the more bird-like Velociraptor. Fossil evidence suggests that these theropods possessed feathers, which probably served various purposes, from thermoregulation to display during mating rituals. As these early feathered dinosaurs evolved, they developed a number of adaptations that made them unique. Over millions of years, they began to show changes in their skeletal structure, including lightweight bones that allowed for more agile movement. Their forelimbs gradually transformed into wings, and their bodies became more streamlined, which were crucial developments for flight. The evolution of an elongated wishbone also played a vital role in strengthening the wing structure, making it more effective for soaring through the air. The extinction event that wiped out the non-avian dinosaurs about 65 million years ago created an opening in the ecological niches of the planet. This event allowed the early birds to thrive and diversify. While many other dinosaur species perished, these avian dinosaurs adapted to new environments and began to develop a remarkable array of species and sizes. from the small sparrows we see today to much larger birds like ostriches. Birds are the living descendants of certain theropod dinosaurs, representing a vibrant lineage that continued to evolve through time. The journey from feathered dinosaurs to modern birds is a testament to the adaptability and resilience of life on Earth, showcasing how dramatic changes in environment and behavior can lead to new forms of existence. Every time we witness a bird in flight, we are witnessing a legacy that stretches back to the age of the dinosaurs, reminding us of the incredible interconnectedness of life and evolution. The extinction event that occurred around 66 million years ago marked the end of the age of dinosaurs, yet some bird-like dinosaurs managed to survive. The traits that contributed to their survival are fascinating, highlighting the unique adaptations that set them apart from their larger, non-avian relatives. One of the defining physical traits of these early birds, which descended from theropod dinosaurs, was their lightweight structure. They possessed feathers, which not only aided in flight but also provided insulation, enabling them to maintain their body heat in rapidly changing environments. The evolution of wings transformed their ability to escape predators and harsh conditions, giving them the agility to navigate through diverse terrains and access new food sources. Additionally, these bird-like dinosaurs exhibited behavioral adaptations that favored survival. They were likely omnivorous, allowing them to consume a varied diet that included seeds, insects, and small animals. This dietary flexibility made them less vulnerable during periods of ecological upheaval when specific food sources became scarce. Their social behaviors, such as flocking, would have offered benefits in terms of navigation and protection against larger predators, enhancing their chances of survival in a chaotic world. Moreover, their reproductive strategies played a role in their resilience. By possibly nesting in more concealed locations and laying multiple eggs, these early birds could increase the likelihood that at least some offspring would survive. Combining these physical characteristics and behavioral traits allowed certain bird-like dinosaurs to thrive amid adversity, eventually leading to the diverse array of bird species we enjoy today. In this way, their legacy continues to soar, a testament to their remarkable adaptability in the face of extinction. The diversification of bird species following extinction events is a fascinating chapter in the story of evolution. To understand this process, we can look back to a significant event, the mass extinction that occurred around 66 million years ago. This event, famously known for wiping out the non-avian dinosaurs, created an opportunity for other species to thrive. With so many ecological niches suddenly available, birds, the descendants of theropod dinosaurs, began to adapt and diversify rapidly. In the aftermath of such extinctions, environments are often drastically altered. This can lead to the emergence of new habitats and food sources, prompting species to evolve unique traits suited to these changes. For birds, this meant adaptations in their size, shape, and feeding behaviors. Brightly colored feathers, varied beak shapes, and different flight abilities allowed birds to exploit a range of ecological roles. For instance, some evolved to become excellent scavengers, while others adapted to become adept fruit eaters. This evolutionary experimentation can be likened to a vast canvas where nature creatively painted diversity. Scientists estimate that over the course of millions of years after the extinction, bird species proliferated into roughly 10,000 different types we recognize today. This is a remarkable example of adaptive radiation, where a single group can evolve into a wide variety of forms that occupy different ecological niches. An outstanding example of this is found in the Galapagos Islands, where a few finch species have diversified into over a dozen distinct forms, each uniquely adapted to its environment. Moreover, the diversification of birds didn't stop with the aftermath of that great extinction. Environmental changes, climatic shifts, and geographical barriers continued to play a pivotal role throughout history. Ice ages, the rise of mountains, and the changing availability of resources have all contributed to an ongoing process of evolution. As we look at the vibrant diversity of birds today, from the graceful hummingbird to the powerful eagle, it becomes clear that their existence is a testimony to resilience and adaptability in the face of change. The evolutionary journey of modern birds is a remarkable tale that stretches back over millions of years, marked by a series of groundbreaking milestones. One of the most significant turning points in this journey occurred during the late Jurassic period, around 150 million years ago, when the small theropod dinosaur Archaeopteryx emerged. Often regarded as the first bird, Archaeopteryx possessed features that merged the world of dinosaurs and the avian realm. It had feathers, a bird-like beak, and wings, yet it also boasted a long tail and claws, typical of its dinosaur ancestors. As time progressed, the evolutionary branch leading to modern birds adapted to various ecological niches. The extinction of the dinosaurs around 66 million years ago was a pivotal moment in Earth's history, and it ushered in a series of remarkable changes in the world of plant life. In the aftermath of this mass extinction event, which wiped out approximately 75% of all species, including the great reptiles, the terrestrial ecosystems underwent a dramatic transformation. With the dinosaurs gone, new opportunities emerged for other organisms to adapt and thrive. One of the most significant shifts in plant life was the evolution and diversification of flowering plants, known scientifically as angiosperms. Before the dinosaurs vanished, the dominant plants were cycads, ferns, and conifers. However, after the extinction, flowering plants began to flourish and spread across the globe. These plants offered more efficient reproductive strategies and a variety of fruit and seeds that attracted different animal species, further facilitating their dispersal. Over time, flowering plants became the predominant type of vegetation, shaping the landscapes we recognize today. This era also marked the rise of grasslands, which played a crucial role in the evolution of many animal species, including mammals. Grasses adapted to hold their own in diverse climates, thriving in areas where ferns and trees previously ruled. This transition not only transformed ecosystems, but also provided essential habitats and food sources for emerging mammals, which began diversifying into a plethora of forms. The interplay between the evolution of grasses and the increase in herbivorous mammals created dynamic ecosystems that fostered further biodiversity. Ultimately, the extinction of the dinosaurs allowed plants to fill unoccupied niches, leading to ecosystems characterized by incredible variety. This evolution impacted not just terrestrial life, but also our climate and the overall health of the planet. Today, angiosperms contribute to the fabric of life on Earth, playing crucial roles in both ecological balance and human agricultural practices. It's a fascinating example of how the end of one era can give birth to a new chapter of life and diversity on our planet. The evolution of flora has always played a pivotal role in shaping ecosystems. As plant life changes, it influences not only the environment, but also the myriad species that depend on it. For instance, when flowering plants began to emerge more than 100 million years ago, they dramatically expanded the available habitats and food sources for various organisms. These changes fostered a complex web of interactions, allowing diverse ecosystems to form. With the introduction of new plant species, ecosystems began to diversify. Different types of flowers and trees created various niches for insects, birds, and mammals. Some species became pollinators, establishing mutualistic relationships with the flowering plants. This interdependence laid the groundwork for more intricate ecosystems where each organism had a vital role. Different zones emerged, such as forests, grasslands, and wetlands, each with its own characteristic plants and animals, demonstrating how flora drives ecological organization. As climate changed over millennia, the adaptive capabilities of plant species further influenced ecosystem dynamics. For example, during periods of warming, certain hardy plants could spread into northern regions, transforming previously barren areas into lush grasslands or forests. These changes not only supported new animal populations, but also increased the complexity of food webs and nutrient cycles within these ecosystems. Moreover, the decline or extinction of particular plant groups can have cascading effects. the loss of a dominant species often leads to reduced habitat diversity, impacting the animal species that rely on those plants for shelter and food. Hence, the continuous evolution and adaptation of flora are not just about survival, they are essential for creating resilient ecosystems that can thrive in the face of environmental changes. The extinction of the dinosaurs, approximately 66 million years ago, marked a pivotal moment in Earth's history. This mass extinction allowed many groups of organisms to flourish, particularly insects and other invertebrates. With the dinosaurs gone, ecological niches that had once been occupied by these large creatures became available. This opened the door for many invertebrates to diversify and expand in ways that were previously unimaginable. Insects, for instance, experienced significant evolutionary changes during this time. The absence of large herbivores meant that plants could grow unchecked, leading to the emergence of new plant species. As these plants diversified, so too did the insects that fed on them. We saw the evolution of new forms, enabling insects to exploit various food sources and habitats. This period also saw the rise of social insects, such as ants and bees, which began to populate the Earth in greater numbers and complexity, forming intricate societies and networks. In addition to insects, other invertebrates such as mollusks and crustaceans also benefited from the newfound opportunities. The oceans became a haven for these creatures, allowing for the expansion of various marine life forms. As ecosystems stabilized and evolved, life in the oceans diversified immensely, leading to the complex underwater environments we recognize today. Coral reefs, teeming with life, became one of the most productive ecosystems on the planet, largely thanks to the thriving invertebrate populations. The end of the dinosaur era was not just the demise of large reptiles, it was a watershed moment for smaller life forms. Through evolutionary adaptation, invertebrates rapidly filled the ecological void left behind, leading to a world rich in biodiversity. The evolutionary paths they took during this period paved the way for the diverse forms of life that still inhabit our planet today. After the mass extinction that occurred approximately 66 million years ago, which famously marked the end of the dinosaurs, the dynamics of predator and prey experienced a remarkable shift. This event, known as the Cretaceous-Paleogene extinction, led to the sudden disappearance of around 75% of Earth's species, including the dominant reptiles of the time. In the wake of this catastrophic scenario, new opportunities emerged for different forms of life. With the extinction of the dinosaurs, smaller mammals began to thrive. These early mammals had previously remained relatively insignificant, but now found themselves in an ecosystem with fewer competitors and predators. This allowed them to diversify and evolve into various forms, eventually giving rise to the mammals we are familiar with today. It was during this period that mammals began to exploit ecological niches that were left vacant, leading to the emergence of new predator and prey relationships. The extinction event also paved the way for birds to flourish. With the dinosaurs gone, these feathered creatures diversified rapidly, evolving into a range of species and occupying roles that their dinosaur relatives once held. Some birds adapted to become effective predators, showcasing remarkable hunting strategies. This new dynamic not only affected terrestrial ecosystems, but also transformed avian hunting in various habitats, from forests to wetlands. On the flip side, the characteristics of the prey species also evolved. Animals that had survived the extinction had to adapt to these new predators. This led to the evolution of different defense mechanisms, such as heightened agility and more sophisticated social behaviors, to evade predators. The extinction catalyzed a significant reset of the ecological balance, fostering a richness of life that would lay the groundwork for the mammals and birds that dominate our world today. After the extinction of the dinosaurs approximately 66 million years ago, the Earth began to experience a dramatic transformation. This period marks the beginning of the Cenozoic era, often referred to as the Age of Mammals. The ecosystems that emerged were profoundly different from those dominated by dinosaurs. Flora and fauna took on new forms and adaptations that helped shape the world as we know it today. One significant characteristic of these new ecosystems was the diversification of mammals. Without the competition from dinosaurs, mammals began to occupy a variety of ecological niches. They evolved into forms ranging from tiny rodents to massive creatures like mammoths. This rapid evolution allowed mammals to thrive in diverse environments, from tropical rainforests to arid deserts. Additionally, birds, which are essentially modern-day dinosaurs, also adapted and evolved into a myriad of species, filling many ecological roles previously held by their extinct relatives. Plants, too, underwent remarkable changes during this time. The warm, humid climates that prevailed in many regions facilitated the spread and diversification of flowering plants or angiosperms. These plants began to dominate landscapes, contributing to more complex ecosystems. The rise of flowering plants not only provided food and habitats for the new mammalian species, but also laid the groundwork for the intricate relationships we observe in modern ecosystems, including those between plants and pollinators. Furthermore, the Cenozoic era experienced significant climatic shifts that influenced the structure of these ecosystems. During the early epochs, the planet was generally warmer, resulting in lush forests and rich biodiversity. However, as the era progressed, the Earth underwent periods of cooling and drying, leading to the development of grasslands and savannas. These changes necessitated adaptations among both mammals and plants, which continuously evolved in response to their changing environments, ultimately giving rise to the rich tapestry of life we see today. The extinction of the dinosaurs around 65 million years ago marked a significant turning point for Earth's ecosystems. With the sudden disappearance of these massive reptiles, various ecological niches were left unoccupied. This opened the door for a new wave of evolution, drastically reshaping the hierarchy of life in different habitats across the globe. In the absence of large dinosaurs, mammals began to diversify and fill roles that had previously been dominated by these reptiles. Smaller mammals, which had adapted to living in the shadows of dinosaurs, now found themselves thriving in diverse environments. Over millions of years, some of these mammals evolved into larger forms, gradually becoming the dominant land animals. This shift allowed mammals to exploit various habitats and resources, leading to a broad spectrum of species and adaptations. Birds also emerged as a notable success story in this new era. Evolving from theropod dinosaurs, they began to fill ecological roles left vacant by their predecessors. With the decline of large predatory dinosaurs, it became possible for birds to flourish. They adapted to a range of lifestyles, from ground foraging to tree dwelling, and they became vital components of food webs, aiding in pollination and seed dispersal. Ultimately, the absence of dinosaurs led to a significant reorganization of ecosystems. The balance shifted toward mammals and birds, which diversified into a wide array of species, each finding its unique place in the food chain. This evolution enriched the complex web of life on Earth, laying the groundwork for the diverse ecosystems we see today. It is a reminder of how interconnected life on this planet really is, and how quickly one group can rise to prominence in the absence of others. After the great extinction event that marked the end of the dinosaurs around 66 million years ago, the world witnessed a dramatic transformation. The vast landscapes that had once been dominated by gigantic reptiles began to evolve into new ecosystems, creating diverse habitats that would be foundational for the life forms that followed. Forests, grasslands, wetlands, and eventually, early versions of modern-day ecosystems emerged, each fostering unique species that would fill the ecological void left by the dinosaurs. Among the notable new habitats were the flowering plant forests. As angiosperms, or flowering plants, became more prominent, they offered rich resources for a variety of life forms. Mammals, which had remained relatively small during the age of the dinosaurs, began to diversify and adapt to these new environments. Species like early primates thrived in these forested areas, taking advantage of the fruits and abundant vegetation that blossomed in the wake of the dinosaurs' disappearance. Grasslands also became prominent during this era, paving the way for the emergence of large herbivores. The adaptation of grasses allowed for the evolution of mammals, such as the early ancestors of horses and elephants. These species developed new grazing habits that allowed them to exploit the vast stretches of grassland, marking a significant shift in animal behavior and ecology. This adaptation brought further diversification, leading to the evolution of many familiar species that we recognize today. Additionally, wetlands and coastal ecosystems started to flourish, attracting a myriad of new species. Birds began to emerge from their feathered predecessors and played an essential role in these new habitats, finding niches that allowed them to thrive. Aquatic environments also saw the rise of diverse fish and amphibians. Overall, the post-dinosaur world became a vibrant tapestry of life, showcasing how resilience and adaptation propelled evolution in ways that shaped our modern biosphere. The extinction event that occurred approximately 65 million years ago, famously known for wiping out the dinosaurs, significantly altered marine ecosystems. Before this event, the oceans were teeming with a variety of organisms, including ammonites, large marine reptiles, and a multitude of fish and coral species. However, with the sudden environmental shifts, including climate change and acidification due to the fallout from a colossal asteroid impact, the consequences for marine life were profound and far-reaching. In the immediate aftermath, many marine species faced extinction, leading to a dramatic reduction in biodiversity. The once dominant ammonites became extinct, as did many species of reef-building corals. These losses created a vacuum in marine ecosystems, disrupting food webs and predator-prey relationships. The extinction also opened up available ecological niches, allowing other organisms to rise and fill these gaps. For instance, fish that could thrive in the altered conditions began to diversify and adapt rapidly, leading to a flourishing of new life forms. Over time, the recovery of marine ecosystems led to the emergence of new species and the re-establishment of reefs. This period marked the ascendance of bony fish, while other marine organisms, such as sharks and rays, began to thrive in these changed waters. The slower-growing, more resilient coral species adapted to the modified conditions began to form new reefs, providing habitats for various marine life once again. This resilience illustrates the ocean's capacity to adapt and evolve following catastrophic events. As millions of years passed, these transformations set the stage for the rich marine biodiversity we observe today. The patterns of life that evolved in these post-extinction waters not only demonstrate the resilience of ecosystems, but also highlight the intricate connections within marine environments. Thus, from devastation arose a new tapestry of life, reinforcing how nature can heal and reinvent itself after catastrophic change. The extinction of the dinosaurs, roughly 66 million years ago, set off a cascade of geological changes that dramatically transformed our planet. This event, widely attributed to a massive asteroid impact in present-day Mexico, not only led to the immediate annihilation of about 75% of all species, but also shifted the course of Earth's geological and biological evolution. In the wake of this cataclysm, the environment underwent profound changes. The impact would have generated intense heat and massive wildfires, followed by a nuclear winter effect, with dust particles and soot blocking sunlight for an extended period. This drastic reduction in sunlight caused dramatic temperature drops and altered weather patterns, resulting in shifts in the landscape. As ecosystems collapsed, the remaining plant life struggled, paving the way for new geological formations as ancient seas receded and new land contours emerged. Millennia later, as temperatures gradually stabilized, Earth began to flourish again. With the mass extinction of dominant reptilian species, mammals and flowering plants began to diversify and proliferate. The breakup of the supercontinent Pangaea continued, leading to the formation of modern continents, which in turn shaped oceanic currents and climate. The groundwork was laid for the emergence of new habitats, allowing a different set of species, including mammals, to thrive and evolve. Volcanic activity during this period also played a significant role in reshaping Earth's landscapes. The Deccan Traps in India, a series of massive volcanic eruptions contemporaneous with the extinction event, altered regional geology, contributed to climate change, and released vast amounts of carbon dioxide into the atmosphere. These geological shifts marked the start of the Cenozoic era, a geological epoch that continues to shape our world and influence life on Earth to this day. This transformation carved out a new planetary narrative, redefining the evolutionary path of the ages to follow. The evolution of Earth's atmosphere is a remarkable story of transformation shaped by geological processes, biological activity, and cosmic events. Initially, when our planet formed about 4.5 billion years ago, the atmosphere was inhospitable. It was filled with gases such as hydrogen, helium, and volcanic emissions, including carbon dioxide, methane, and ammonia. However, this primordial atmosphere could not support life as we know it, and was eventually stripped away by solar winds, particularly in the absence of a protective magnetic field. As the Earth cooled, volcanic activity started to play a crucial role in rebuilding the atmosphere. Gases released from volcanoes contributed to the development of a new atmosphere dominated by carbon dioxide and water vapor, with traces of nitrogen and other gases. This was not a stable configuration, as Earth continued to experience significant temperature variations and conditions suitable for dramatic climate shifts. During this period, the planet underwent a process known as outgassing, where materials from deep within the Earth released gases into the atmosphere. The next major turning point came with the appearance of photosynthetic organisms, which began to thrive around 2.5 billion years ago. Tiny microorganisms, including cyanobacteria, transformed carbon dioxide into oxygen through a process that harnesses sunlight. Over millions of years, this gradual but significant shift led to the accumulation of oxygen in the atmosphere, a transformation known as the Great Oxidation Event. This dramatic increase in oxygen not only changed the composition of the atmosphere, but also paved the way for more complex life forms to evolve. The atmosphere continued to evolve over time as factors such as plate tectonics and biological evolution influenced its composition. By regulating gases like oxygen and carbon dioxide, Earth's systems have kept our atmosphere in a balance that supports life. Today, we breathe an atmosphere that is roughly 21% oxygen and 78% nitrogen, a far cry from its volatile beginnings. Understanding this dynamic evolution helps us appreciate the delicate equilibrium that allows life to thrive on our planet. As the Earth's atmosphere has undergone significant changes over time, these alterations have had notable impacts on global temperatures and weather patterns. From fluctuations in greenhouse gas levels to shifts in ocean currents, the intricate balance of our climate system has been affected in ways that resonate across the planet. Historically, periods of high volcanic activity, for instance, have introduced large amounts of ash and gas into the atmosphere, temporarily cooling the Earth and altering normal weather patterns. One of the most pervasive changes has been the rise in greenhouse gases due to human activities, particularly since the Industrial Revolution. Carbon dioxide, methane, and nitrous oxide are now at levels not seen for millions of years. These gases trap heat from the sun, leading to an overall increase in global temperatures, a phenomenon widely known as global warming. This warming is not uniform, rather, it results in a variety of effects such as more intense heat waves, shifting rainfall patterns, and altered seasons. As global temperatures rise, so do sea levels, largely due to the melting of polar ice sheets and glaciers. The consequences are profound and include increased flooding in coastal areas and the displacement of communities. In addition, warmer oceans contribute to the intensification of storm systems, leading to more powerful hurricanes and typhoons. Regions that once had predictable weather systems are now experiencing surprising droughts or deluges, influencing agriculture, water supplies, and natural ecosystems. In conclusion, the atmospheric changes humanity has driven are intricately linked to the alterations in climate and weather patterns we observe today. Understanding these relationships not only aids in grasping the current state of our planet, but also emphasizes the urgent need for action to mitigate these changes. The natural world is profoundly interconnected, and even minor shifts can ripple through the very fabric of our climate system, reminding us that careful stewardship of the environment is essential for future generations. Throughout Earth's history, significant changes have occurred in climate, glacial activity, and sea levels, all of which greatly influenced ocean circulation. As glaciers and ice sheets melted during periods of warming, vast amounts of fresh water poured into the oceans. This contributed to rising sea levels, altering coastlines around the world, and submerging various land areas that were once thriving ecosystems. This influx of fresh water did not just raise sea levels, it disrupted the delicate balance of ocean currents. The oceans are interconnected systems where warmer water normally rises and moves toward the poles, while colder water sinks and flows back toward the equator. When large quantities of fresh water entered the oceans, it weakened the salinity or saltiness of seawater in those areas. This change in salinity can affect the density of the water, which is crucial for driving ocean currents. Consequently, these currents were slowed or altered, which has repercussions on global climate patterns. Additionally, shifts in sea levels and ocean circulation can impact weather patterns and contribute to the severity of storms. Ocean currents play a vital role in redistributing heat around the planet. When these patterns change, regions may experience unusual weather. Some may become cooler and wetter, while others could face droughts and more intense storms. This can affect not only the environment, but also agriculture, drinking water supplies, and the overall health of marine ecosystems. Throughout Earth's timeline, these dynamic shifts have had cascading effects on the planet's biology. Marine life depends heavily on specific temperature and salinity ranges. As conditions shift, ecosystems adapt, migrate, or sometimes face extinction, causing ripple effects throughout the food chain. Understanding these interconnected changes is essential as we navigate current and future climate challenges. The extinction of dinosaurs around 66 million years ago marked a pivotal turning point in Earth's history. This massive event, likely triggered by a cataclysmic asteroid impact, wiped out nearly 3/4 of all species, creating a world in upheaval. While this catastrophe spelled the end for dinosaurs, it opened up a myriad of ecological niches for smaller mammals and other life forms to thrive and diversify. In the aftermath of the dinosaurs' demise, mammalian species, which had been small and relatively inconspicuous during the age of dinosaurs, began to flourish. With fewer competitors and predators, these mammals adapted to various environments and developed new traits. Over the following millions of years, this diversification led to the evolution of a wide range of species, including primates, the ancestors of modern humans. The flexibility and adaptability shown by early mammals were crucial as they gradually filled the ecological roles previously held by larger reptilian species. As mammals evolved, changes in climate and environment further shaped their development. For primates, the transition to tree-dwelling lifestyles introduced challenges and opportunities that promoted increased intelligence and social behavior. The ability to navigate complex social structures became a significant advantage, and traits such as problem-solving skills, communication, and tool use emerged, laying the groundwork for the evolution of modern humans. The extinction of dinosaurs not only ended an era, but also paved the way for mammals to dominate. This shift set into motion a series of evolutionary changes that eventually led to the rise of humans. Our lineage can be traced back to this dramatic moment in history, reminding us how interconnected life on Earth truly is, even across the vast epochs of time. The story of primate evolution unfolds dramatically in the aftermath of a significant extinction event around 66 million years ago, which notably wiped out the dinosaurs. As the world transformed, new opportunities arose for mammals, including the early ancestors of primates. These small tree-dwelling creatures gradually evolved, adapting to varied habitats and lifestyles in the lush forests that flourished during this time. By the time we reach the Eocene epoch, approximately 56 million years ago, we see the emergence of the first true primates, known as primate ancestors or euprimates. This group included species that showcased key adaptations such as grasping hands, forward-facing eyes for better depth perception, and a larger brain relative to body size. These adaptations allowed them to thrive in the complex arboreal environment where navigating branches and foraging for fruits and insects was crucial for survival. As we move into the Oligocene epoch, around 34 million years ago, we witness the appearance of the first anthropoid primates. These ancient relatives would eventually give rise to the monkeys, apes, and humans we know today. This era saw the emergence of two major lineages: the New World monkeys in South America, known for their prehensile tails, and the Old World monkeys and apes in Africa and Asia. This split is significant as it heralded a diversification that responds to different ecological niches and food resources available in their regions. Finally, the evolution of hominins, our direct ancestors, began during the Miocene epoch around 23 million years ago. This period brought about significant developments, such as bipedalism, walking on two legs, which set us apart from other primates. Over millions of years, these hominins evolved, adapting their traits and behaviors, leading eventually to the emergence of Homo sapiens. Throughout this incredible journey, we can trace the threads of evolutionary change that illustrate both our connection to the broader primate family and our unique place in the tree of life. The evolution of early hominins is intimately tied to the changing landscapes of our planet. As continents drifted and climates shifted, the environments in which our ancestors lived transformed dramatically. About 6 million years ago, the Earth experienced significant fluctuations, with some areas becoming arid while others morphed into lush forests. These changes prompted early hominins to adapt, influencing their morphology, behavior, and survival strategies. One of the most pivotal landscape changes was the transition from dense forests to more open savannas. As forests receded, early hominins, such as Australopithecus, found themselves in environments where they needed to travel greater distances for food and resources. This shift encouraged the development of bipedalism, walking on two legs, which offered advantages in energy efficiency and improved visibility over tall grasses. Standing upright not only helped them spot predators, but also allowed them to forage more effectively. Changes in ecosystems also had profound implications for the diet of early hominins. As the landscape evolved, the diversity of available plants and animals shifted, pushing hominins towards more flexible foraging strategies. They began to consume a broader array of foods, including tubers, fruits, and eventually meat. This dietary diversification was crucial, enhancing cognitive development and paving the way for more complex social behaviors as groups began to share resources and collaborate in hunting. Furthermore, the climates of different regions created various challenges and opportunities that further influenced evolution. In response to the harsh environments of the savanna, early hominins developed tools and adapted their social structures to improve their chances of survival. As different groups ventured into new territories, they encountered unique flora and fauna, leading to the diverse adaptations we see in hominin species today. The interplay between evolutionary changes and the dynamic Earth shaped the path of human development, illustrating how our ancestors thrived amid shifting landscapes. After the age of dinosaurs came to a dramatic end about 66 million years ago, Earth underwent significant transformations. The mass extinction that wiped out the dinosaurs opened ecological niches that early mammals could exploit. For our ancestors, the challenges of survival in these new environments pushed them toward remarkable adaptations. As the world transitioned from dense forests to more open plains, these early mammals began to diversify and evolve in ways that would lay the groundwork for future generations. The climate also shifted, presenting our ancestors with both obstacles and opportunities. With the cooling of the earth and changes in vegetation, early mammals developed traits suited for varied environments. For example, some species became more agile and faster, which allowed them to escape predators and hunt more efficiently. Others adapted by developing social structures that helped in foraging, taking advantage of group dynamics for protection and resource acquisition. As time progressed, the evolution of distinct features became crucial for survival. These ancestors relied on their sense of smell and developed larger brains relative to body size, enhancing their cognitive abilities. This intelligence allowed early humans to create tools, harness fire, and communicate effectively within groups. These advancements not only contributed to their survival, but also led to the establishment of intricate social networks that were vital in the often harsh environments of the post-dinosaur world. The gradual evolution of bipedalism, walking on two legs, further distinguished our ancestors from other mammals. This adaptation not only freed their hands for tool use, but also improved their ability to traverse varied terrains. As they learned to thrive in open savannas and diverse habitats, these adaptations set the stage for the emergence of Homo sapiens and the complex societies that would follow, highlighting the resilience and ingenuity of early life in a changing world. The Paleocene-Eocene thermal maximum, often abbreviated as the PETM, occurred around 55 million years ago. This extraordinary event lasted approximately 100,000 years and is characterized by a dramatic rise in global temperatures, estimated to be about 6 degrees Celsius. Such a significant increase has profound implications for both the environment and biodiversity, setting the stage for rapid changes in ecosystems around the globe. During the PETM, the warming was largely driven by an influx of carbon into the atmosphere, releasing vast quantities of greenhouse gases, mainly carbon dioxide and methane. This change in climate corresponded with considerable alterations in habitats, affecting weather patterns and oceanic conditions. As temperatures rose, many species were forced to adapt or migrate to cooler areas, changing the distribution of flora and fauna. The PETM acted as a catalyst for ecological transformation. The impact on biodiversity during this time was remarkable. Many species benefited from the warmer temperatures, leading to an evolutionary explosion in some groups. Mammals, in particular, diversified extensively, taking advantage of the lush, temperate conditions. This period saw the evolution of many modern mammal families, indicating that while some species went extinct, others thrived, paving the way for the mammals we are familiar with today. However, not all ecosystems fared well. Some marine life, such as certain calcifying organisms, struggled to cope with the changing conditions, leading to a significant loss of biodiversity in the oceans. In understanding the significance of the Paleocene-Eocene thermal maximum, we see a clear illustration of how climate can drive evolutionary changes, shaping ecosystems and influencing the diversity of life on Earth in both positive and negative ways. The Paleogene period, which lasted from about 66 million to 23 million years ago, followed one of the most significant extinction events in Earth's history. This marked the end of the dinosaurs and set the stage for an extraordinary recovery of biodiversity. As the dust settled from the cataclysm that ended the reign of the dinosaurs, the ecosystems began to flourish with newfound vigor. During this time, mammals, which had previously occupied the role of small, sometimes overlooked creatures, rapidly diversified. Without the dinosaurs to dominate the land, mammals adapted to fill various niches. They evolved into forms ranging from the size of a mouse to formidable beasts like early whales. This expansion laid the foundation for modern mammals, showing remarkable variability from species that would become the ancestors of present-day elephants to those resembling today's primates. Meanwhile, plants also underwent a significant transformation. Flowering plants, or angiosperms, spread extensively during the Paleogene. Their adaptation to different environments allowed them to thrive, providing crucial habitats and food sources for the burgeoning populations of mammals and birds. The warming climate and the opening up of various ecosystems, such as forests and grasslands, created rich landscapes where diverse life forms could proliferate. The Paleogene period served as a remarkable chapter in the story of life on Earth, where the ripple effects of the extinction event allowed new forms of life to emerge and flourish. The interplay between evolving mammals, the expansion of flowering plants, and changing climates set the stage for the complex biodiversity that we witness today. It was truly a time of rebirth and transformation for life on our planet. The extinction of the dinosaurs around 66 million years ago marked a pivotal moment in Earth's history, opening the door for a remarkable transformation of our planet's ecosystems. With the dinosaurs removed from the picture, myriad habitats became available for colonization. This mass extinction event allowed smaller animals, particularly mammals and birds, to explore and fill these vacant ecological niches. In the aftermath of this extinction, evolution kicked into high gear. Species that had previously been overshadowed began to adapt and diversify, taking advantage of the resources left behind. Mammals, which had been small and mostly nocturnal during the age of dinosaurs, began to grow and develop unique traits suitable for diverse environments. This included adaptations for flight in some mammalian species, leading to the rise of bats and other forms of life that would not have thrived in a world dominated by large reptiles. The inventive process of evolution flourished in this newly available space. Over millions of years, mammals evolved into a wide range of forms, from whales navigating the oceans to elephants roaming the savannas. Meanwhile, flowering plants blossomed in the absence of heavy herbivores, creating more habitats and food sources. This effectively set a stage for animals to evolve that would specifically fill roles vacated by dinosaurs, like the large herbivores and apex predators. When the dinosaurs disappeared, the stage was set for an explosion of life, with new species venturing into previously unoccupied niches. This evolutionary journey not only transformed the roles that animals played within ecosystems, but also played a vital role in shaping the rich tapestry of life that we see today. To understand the most successful animal lineages that emerged during this remarkable period in Earth's history, we first look back at the era known as the Cambrian, around 500 million years ago. This was a transformative time when life exploded in diversity and complexity. Among the standout lineages were the arthropods, mollusks, and echinoderms. Arthropods, which include ancestors of today's insects, spiders, and crustaceans, showcased incredible adaptability. Their hard exoskeletons provided protection and support, while jointed limbs allowed for a range of movement. This versatility set the stage for their domination in various environments, which continues to this day, with insects alone comprising over 1 million described species. Mollusks also rose to prominence during this period. With their soft bodies and diverse forms, they adapted to various ecological niches. Some developed hard shells, like the ancestors of modern clams and snails, while others, like the early cephalopods, evolved remarkable intelligence and mobility. Their evolutionary success is evident in the fact that mollusks remain one of the most diverse groups of animals on the planet. Lastly, echinoderms, including sea stars and sea urchins, showcased unique features like radial symmetry and a water vascular system for movement and feeding. They thrived in marine environments and played important roles in ecosystem dynamics. This early diversification laid the foundation for the complex biological communities we see today, illustrating the incredible resilience and adaptability of life on Earth. The Cambrian explosion was indeed a pivotal moment that set the stage for the rich tapestry of life that would follow. The extinction of the dinosaurs marked a significant pivot point in Earth's history, ushering in a new era for life on our planet. In the wake of this mass extinction, which occurred around 66 million years ago, a remarkable recovery and diversification of species took place. Recent technological advancements have vastly improved our ability to study this period, helping scientists uncover the complex web of life that emerged in the aftermath of the dinosaurs' disappearance. One of the most transformative tools has been advanced imaging techniques, such as computed tomography scans, which allow paleontologists to examine fossils in unprecedented detail without damaging them. Through these scans, researchers can virtually dissect fossils and uncover hidden structures, revealing insights about anatomy and behavior. This non-invasive method has opened up new avenues for understanding the evolutionary pathways that led to the rise of birds, mammals, and other groups following the extinction event. In addition to imaging, the development of powerful dating techniques has revolutionized our grasp of post-dinosaur timelines. Methods like radiocarbon dating and luminescence dating enable scientists to accurately determine the ages of ancient sediments and fossils. This precision helps researchers piece together the chronology of life on Earth, marking key events and transitions, such as the rise of flowering plants and the migration of early mammals, thereby painting a clearer picture of ecological recovery after the mass extinction. Furthermore, genomic analysis and ancient DNA technologies have provided astonishing insights into how species evolved in response to changing environments. By studying the genetic material of ancient organisms, scientists can trace lineages and understand how life adapted to the new conditions of a post-dinosaur world. Together, these technological advances are not just enhancing our knowledge of this intriguing chapter in Earth's history, they are revealing a dynamic and resilient story of survival, adaptation, and evolution that continues to captivate the scientific community and curious minds alike. In the study of ancient life, dating fossils plays a crucial role in understanding the events surrounding extinction, particularly when it comes to the mass extinction that wiped out the dinosaurs approximately 66 million years ago. Traditional methods, such as radiometric dating, rely on the decay of radioactive isotopes in rocks. However, advancements in technology have introduced new and innovative methods that provide more precise dating of fossils from this pivotal time period. One of the notable methods is the use of a technique called luminescence dating. This method measures the last time quartz or feldspar minerals were exposed to sunlight. When these minerals are buried, they accumulate energy from background radiation over time. By analyzing these minerals within sediment layers above or below fossilized remains, scientists can establish a time frame for when the organisms lived, effectively placing a date on the fossils based on their burial context. Another emerging technique is known as argon-argon dating. This method is particularly useful for dating volcanic layers associated with fossil finds. When a volcanic eruption occurs, it releases gases that include argon, which can be measured in volcanic rock. By comparing the ratio of radioactive argon to stable argon, researchers can ascertain the age of the volcanic ash layers and subsequently the age of the fossils embedded within those layers. This method helps create robust timelines that connect fossils directly to the events surrounding their extinction. Furthermore, paleomagnetic dating has gained traction. As sediments settle, tiny magnetic minerals within them align with the Earth's magnetic field. By examining these magnetic orientations and comparing them to known shifts in Earth's magnetic field, scientists can estimate the age of sediment layers that contain fossils. Using these diverse methods allows for a multifaceted approach to dating fossils. Such advancements in dating techniques continue to deepen our understanding of extinction events and the life forms that characterize those ancient ecosystems. Paleontologists, the scientists who study fossils, have developed a fascinating array of techniques to reconstruct ancient climates and environments. Understanding what the Earth was like millions of years ago relies heavily on examining physical evidence left behind in the geological record. By carefully analyzing fossils ranging from plants to animals, paleontologists can gather clues about historical ecosystems and climate conditions. One method used in these reconstructions is the examination of plant remains. For instance, the presence of leaf shape and size can indicate past climate conditions. Some plants thrive in warm, humid environments, while others are adapted to cold or dry conditions. By identifying the types of plants that existed during certain periods, researchers can infer the climate at that time. Additionally, sediment cores taken from lakes and ocean beds provide valuable environmental data, revealing shifts in temperature and precipitation patterns. Another effective approach involves the study of isotopes, which are variants of chemical elements. Isotopes of oxygen and carbon found in fossilized shells or ice cores can supply information about temperature and atmospheric conditions. For example, when the climate is warmer, the ratios of these isotopes change, providing insights into Earth's temperature history over millions of years. These changes can be cross-referenced with records from other geological samples, creating a more detailed picture of ancient environments. Ultimately, by piecing together these diverse strands of evidence, paleontologists can reconstruct not only the climate, but also the ecological interactions at play during different geological periods. This knowledge is crucial for understanding how life on Earth has adapted to changing climates over time and provides context for contemporary climate dynamics. Such explorations remind us that the history of our planet is etched in the very fabric of the Earth, waiting to be uncovered through the diligent work of scientists. Modern imaging techniques have revolutionized our understanding of life after the age of dinosaurs, providing scientists with detailed insights that were previously unimaginable. One of the most significant advancements is computed tomography, commonly known as CT scanning. This technology allows researchers to visualize the interior structures of fossils without damaging them. By creating highly detailed, three-dimensional images, scientists can study the anatomy of ancient creatures, revealing their physical adaptations and evolutionary pathways in detail. In addition to CT scanning, techniques like X-ray fluorescence and infrared spectroscopy have also made substantial contributions. X-ray fluorescence enables scientists to analyze the elemental composition of fossils and sediments, providing clues about the environment in which these organisms lived. Infrared spectroscopy helps identify organic compounds preserved in fossils, offering insights into the diets and habitats of creatures that thrived during the post-dinosaur era. Together, these methods have illuminated the transition from a world dominated by reptiles to one shaped by mammals and birds. Furthermore, advancements in digital modeling and reconstruction techniques have enabled paleontologists to simulate ancient ecosystems. These simulations can visualize interactions between species and understand how environmental changes influenced evolution. For instance, during the initial stages of the Cenozoic era, the climate shifted significantly, impacting plant growth and animal life. By analyzing how different species adapted to changes in their environment through this new technology, scientists can piece together a clearer timeline of evolutionary developments. Modern imaging techniques have transformed our ability to examine fossils and trace the lineage of life forms after the dinosaurs. This combination of technology has not only provided a window into the past, but also enriched our comprehension of evolutionary biology, helping to explain how today's diverse range of animal and plant life emerged from the ashes of the dinosaur era. Each discovery illuminates a chapter in the history of life on Earth, inviting us to appreciate the intricate tapestry of evolution that has unfolded over millions of years. The extinction of the dinosaurs around 66 million years ago set the stage for significant changes in both plant and animal life. With the dominant dinosaurs gone, mammals began to evolve and diversify, leading to a new chapter in the history of life on Earth. As mammals expanded into vacant ecological niches, they interacted in fascinating ways with the plant life that was also undergoing shifts. One of the pivotal changes was how plant species adapted to the absence of large herbivores like the dinosaurs. This created opportunities for flowering plants to thrive and diversify. Insects, particularly, played a critical role in pollination, helping the emergence and establishment of new plant species. As these flowering plants evolved, they offered diverse food sources, which in turn attracted a variety of herbivorous mammals. The relationship blossomed into a complex web of interdependencies, where the survival of one often hinged on the other. Simultaneously, the mammals began exhibiting behaviors that changed their environments. As they fed on plants, they influenced plant growth patterns and seed dispersal. For instance, Many plant species evolved fruits or seeds that required animals for their dispersal, leading to a continued evolution of both flora and fauna. This mutualistic relationship helped shape ecosystems and paved the way for the intricate balance we see today. Thus, the aftermath of the dinosaurs' disappearance was not merely a plant and animal survival scenario. Instead, it ignited a fascinating interplay of adaptation, evolution, and mutual influence that reshaped life on Earth. The interactions that sparked from this period laid the groundwork for ecosystems as we know them, revealing a remarkable tale of resilience and transformation in the natural world. Following the extinction of the dinosaurs around 66 million years ago, Earth experienced a dramatic shift in its ecological landscapes. This mass extinction opened up myriad niches and environments, leading to a flourishing of new species. Competition among these emerging creatures became a powerful catalyst for evolution, driving species diversity in what is known as the Cenozoic era, often referred to as the Age of Mammals. In the wake of the dinosaurs' disappearance, mammals diversified significantly. With fewer predators and competitors dominating the landscapes, mammals were free to explore different ecological roles. Some began to adapt to arboreal lifestyles in the trees, while others took to the open plains or developed burrowing habits. This diversification was fueled by competition as species vied for resources such as food, shelter, and mating opportunities. Those that could exploit available resources more efficiently or adapt to changing environments gained an advantage, gradually leading to a broad spectrum of mammalian forms. Birds, too, capitalized on this competitive environment. With the downfall of their dinosaur relatives, they adapted to fill in ecological gaps, exploring unoccupied niches. This led to the emergence of various bird species with diverse diets and habitats, from raptors soaring through the skies to ground-feeding species scattered across fields and forests. The competition for resources pushed these creatures to innovate and specialize, resulting in the remarkable avian diversity we see today. In this dynamic interplay of competition and adaptation, we see the intricate dance of evolution at work. Species that adapted successfully not only survived, but also thrived, leading to rich and diverse ecosystems. This thriving of life following the dinosaurs illustrates the inherent resilience of nature, driven by competition to fill ecological vacancies and expand the tapestry of life on Earth. The legacy of this evolutionary explosion continues to resonate in contemporary biodiversity, reminding us that competition, while often fierce, can also be a tremendous driver of innovation in the natural world. In the ever-changing landscapes of our planet, symbiotic relationships have thrived, showcasing the intricate connections between various species. These relationships can take on several forms, but predominantly they fall into three categories: mutualism, commensalism, and parasitism. Each type highlights the fascinating interdependence that unfolds within ecosystems, revealing how life adapts and evolves in the face of change. One shining example of mutualism can be found in the vibrant relationship between flowering plants and their pollinators, such as bees and butterflies. As these pollinators search for nectar, they inadvertently transfer pollen from one bloom to another, facilitating the reproduction of plants. Not only do the plants benefit from increased reproduction, but the pollinators receive a rich food source, illustrating a beautiful balance where both parties gain from the interaction. Another striking symbiotic relationship is found in the world of corals and the algae known as zooxanthellae. These tiny algae live within the tissues of corals and perform photosynthesis, providing essential nutrients for their hosts. In return, the corals offer the algae a protected environment and access to sunlight. This partnership is pivotal for the health of coral reefs, which serve as vital ecosystems for countless marine organisms. In contrast, parasitism presents a relationship where one organism benefits at the expense of another. Take the case of tapeworms in the intestines of various animals. These parasites absorb nutrients from their host, often leading to health issues for the host while allowing the tapeworm to thrive. While these relationships may seem detrimental, they play an essential role in maintaining balance within ecosystems by regulating populations and encouraging evolutionary adaptations. These symbiotic interactions are remarkable reminders of the complexity and interconnectedness of life on Earth. Species have always interacted with their environments in dynamic ways, influencing the ecosystems they inhabit. These interactions include competition for resources, predator-prey relationships, and symbiotic partnerships. As environments evolve, whether due to climate change, geological shifts, or human activity, species must adapt or migrate. This adaptability is a key driver for creating new ecosystems. For instance, when changes occur in temperature or precipitation, some species may migrate to more suitable habitats, while others must adapt to the shifting conditions. This can lead to the emergence of new traits and behaviors. A classic example is the Galapagos finches, which adjusted their feeding habits and body sizes in response to variations in food availability due to changing climates over generations. Such adaptations help maintain balance within ecosystems even as conditions change dramatically. Moreover, species interactions also include the process of ecological succession. When a disturbance occurs, such as a forest fire or a volcanic eruption, the affected area is often colonized by opportunistic species first. As these species thrive, they create conditions that allow other organisms, like shrubs and trees, to establish themselves, ultimately leading to a mature ecosystem. This gradual development showcases how different organisms can reshape their environments, fostering a diverse web of life. The interplay between species and their changing environments is complex and continuous. Through these interactions, ecosystems are not only resilient, but also capable of evolving into new forms. This ongoing cycle of adaptation and change highlights the intricate relationship between life and the planet, revealing the remarkable adaptability of nature in the face of change. After the age of the dinosaurs came to a dramatic close around 66 million years ago, reptiles faced a transformed world. With the extinction of the dinosaurs, multiple niches in the ecosystem opened up. This newfound opportunity allowed reptiles to adapt and thrive in various forms. Notably, the survivors of this cataclysm included ancestors of modern reptiles, which would diverge into several distinct lines. One of the most remarkable adaptations was seen in the turtles. Some turtles developed a protective shell, which aided their survival as they retreated to water bodies and became adept swimmers. This adaptation allowed them to escape from land predators and flourish in aquatic environments. The diverse habitats they occupied led to a wide variety of turtle species, each perfectly suited to its particular ecological niche. Furthermore, lizards and snakes also emerged as significant winners in post-dinosaur ecosystems. Many lizards adapted to their environments by developing specialized colors and patterns which helped them blend with their surroundings, providing camouflage against predators. Snakes, having evolved from lizard ancestors, adapted by losing their limbs. This elongated form allowed them to navigate through dense underbrush and even swim in water, expanding their hunting territories significantly. As the Earth warmed during the age that followed, reptiles diversified even further, leading to the emerging species we recognize today. Some of these adaptations were so effective, they enabled reptiles to occupy a wide range of habitats, from deserts to rainforests. In this post-dinosaur era, reptiles did not merely survive, they evolved into a cornerstone of Earth's biodiversity, showcasing remarkable resilience and adaptability. After the mass extinction that occurred around 65 million years ago, amphibians underwent significant evolutionary developments that shaped their diversity and adaptation to new environments. This event marked the end of the last great age of reptiles and opened up ecological niches, allowing amphibians to thrive and evolve in ways that were previously unimagined. One of the most notable developments was the diversification of amphibian species. With many competitors and predators gone, amphibians began to occupy various habitats, including forests, wetlands, and other terrestrial environments. This adaptability was crucial as they evolved to exploit available resources. Over time, new frog, toad, and salamander species emerged, showcasing a wide range of sizes, colors, and behaviors. This diversification was not just a survival tactic, it was a testament to nature's ability to fill ecological voids left by extinction. Another major development was the refinement of their reproductive and developmental strategies. Some amphibians shifted from reliance on stagnant bodies of water for breeding, typically prone to drying out, to more versatile breeding strategies. This led to adaptations such as direct development, where some species bypass the larval stage altogether. By laying eggs on land or in ephemeral pools, amphibians significantly improved their chances of survival, especially in changing climates. Furthermore, amphibians began to develop complex social behaviors and interactions. This included vocal communication, as seen in singing frogs and toads, which became essential during mating seasons. These intricate interactions not only helped them find mates, but also influenced predator-prey dynamics. In this post-extinction world, amphibians emerged as a vital part of the ecosystem, evolving into a diverse and resilient group that continues to captivate our interest today. After the mass extinction event that wiped out the dinosaurs around 66 million years ago, Earth's ecosystems were profoundly altered. This extinction opened up various ecological niches, allowing marine life, particularly fish, to thrive and evolve in ways that had not been possible before. With less competition and a drastically different environment, fish populations began to diversify rapidly. In the aftermath, various groups of fish adapted to these new aquatic environments. One notable transformation involved the proliferation of bony fish, which are characterized by their bony skeletons, as opposed to the cartilaginous skeletons found in sharks and rays. These bony fish quickly filled the ocean's niches, adapting to different habitats and food sources. For instance, some species evolved to become more efficient predators, while others developed specializations that allowed them to graze on algae or consume plankton. Furthermore, this period saw the rise of unique adaptations in morphology and behavior. Some fish developed enhanced camouflage to evade predators, while others showcased vibrant colors to attract mates or communicate. The evolution of specialized fin structures permitted better maneuverability and speed, making it easier for these species to thrive in various environments, from the open ocean to intricate reef systems. Through millions of years of evolution, fish populations not only regained their numbers, but also emerged with a stunning diversity that contributed to the aquatic tapestry we see today. This evolutionary response highlights the remarkable resilience of nature and its capacity to adapt following significant ecological disturbances, forever shaping the underwater world and the balance of marine ecosystems. The evolution of birds is a fascinating tale that traces back to ancient ancestors. Among the most significant trends observed in large birds and early flightless avian species is the adaptation to their environments. Over millions of years, certain birds evolved to become larger, which provided them with various advantages, such as enhanced thermoregulation and the ability to travel long distances in search of food. In many cases, larger size also meant fewer natural predators, allowing these birds to thrive in various habitats. Another critical aspect of this evolutionary journey is the development of flightlessness in some avian species. Birds like ostriches, emus, and kiwis have simplified wing structures over time as they adapted to terrestrial lifestyles. This shift often occurs because, on certain islands or isolated environments, the benefits of flight diminish. These birds have instead evolved powerful legs that allow them to run quickly and escape terrestrial threats. Flightlessness often corresponds with the absence of predators in their habitats, enabling these birds to exploit resources on land without needing to take to the skies. Interestingly, the loss of flight does not mean these species lost the ability to navigate their world. Flightless birds have developed other skills, such as enhanced foraging abilities and unique reproductive strategies that suit their ground-dwelling lifestyles. This evolutionary branch illustrates how life can adapt to fill ecological niches, showcasing the diversity within avian species. Finally, the study of these evolutionary trends not only illuminates the past, but also highlights the potential future of birds in changing environments. As climates shift and habitats are altered, understanding the adaptations of large and flightless birds helps scientists predict how these avian species may respond. This ongoing journey of evolution is a testament to the resilience and adaptability of life on Earth, inviting us to ponder what new forms and behaviors future generations may witness. After the reign of the dinosaurs ended around 66 million years ago, Earth witnessed several significant extinction events that shaped the course of life on our planet. One of the most notable is the Paleocene-Eocene thermal maximum, which occurred approximately 55 million years ago. This event was characterized by a rapid rise in global temperatures, likely driven by intense volcanic activity and the release of greenhouse gases. During this time, many species struggled to adapt to the sudden climate changes, leading to widespread extinctions, particularly among marine life. Moving forward in time, around the end of the Permian period, we encounter the Great Dying, which took place approximately 252 million years ago. Though it occurred before the age of dinosaurs, its legacy can still be felt in the evolutionary pathways that followed. It wiped out up to 97% of all marine species and a significant portion of terrestrial life. The causes remain a topic of investigation, but massive volcanic eruptions, climate shifts, and changes in ocean chemistry all play a role in this catastrophic event. Another crucial extinction event took place during the late Cretaceous period, continuing to impact life long after the dinosaurs vanished. This event, known as the Tertiary Paleogene extinction event, led to the extinction of around 3/4 of the Earth's species, including all non-avian dinosaurs. This massive die-off opened up ecological niches that allowed mammals to flourish and eventually dominate terrestrial ecosystems. Lastly, more recent is the Quaternary extinction event, which occurred during the last ice age, around 12,000 years ago. This period saw the extinction of many large mammals, such as woolly mammoths and saber-toothed cats. While climate change played a significant role, human activities like hunting also contributed significantly to the decline of these majestic creatures. Each of these extinction events reshaped ecosystems, paving the way for new species to emerge and adapt, continually transforming the tapestry of life on Earth. The evolution of life on Earth has been profoundly influenced by significant events over billions of years. One of the key turning points was the emergence of photosynthesis around 3 billion years ago. This groundbreaking process allowed organisms to harness sunlight, converting it into energy and releasing oxygen as a byproduct. As oxygen began to accumulate in the atmosphere, it set the stage for a remarkable transformation. The Great Oxygenation Event fundamentally altered the planet's environment, paving the way for aerobic organisms that thrived in the newly oxygen-rich atmosphere. Another pivotal moment in this narrative was the Permian-Triassic extinction approximately 250 million years ago, often termed the Great Dying. This catastrophic event wiped out about 90% of marine species and 75% of terrestrial species. The aftermath of this mass extinction created a void that led to an explosion of evolutionary innovation. Life began to diversify and adapt to the new conditions, laying the groundwork for the dominance of reptiles and eventually mammals. Just as vital was the impact of continental drift, which has reshaped the planet's geography over millions of years. As land masses shifted, they influenced climate patterns, creating new habitats and leading to the emergence of various species tailored to those environments. For instance, the separation of continents allowed unique ecosystems to develop in isolation, giving rise to the rich biodiversity we observe today. This fluidity in Earth's landscape has continuously sculpted the evolutionary paths of countless organisms. Finally, the impact of natural disasters, such as asteroid strikes, cannot be overlooked in this chronicle. The most famous example, the asteroid that struck Earth around 66 million years ago, is credited with the extinction of the dinosaurs. This event catalyzed the rise of mammals, eventually leading to the evolution of humans. Each of these events, whether cataclysmic or gradual, has played an integral role in shaping the complex tapestry of life that thrives on Earth, demonstrating the interconnectedness of all living things in this grand narrative of evolution. Throughout Earth's history, mass extinctions have reshaped the planet's biodiversity and ecological systems. The study of subsequent extinctions provides keen insights into the resilience of Earth and its ability to recover from catastrophic events. Each extinction event serves as a reminder of life's fragility, but also highlights nature's extraordinary capacity to adapt and evolve in response to changing conditions. For instance, after the well-known dinosaur extinction 66 million years ago, the planet underwent a remarkable transformation. This event cleared the way for mammals to flourish, giving rise to the diverse array of species we see today. These ecological shifts illustrate how life can rebound and evolve, filling niches left vacant by extinct species. It's a powerful testament to the inherent resilience of life, as ecosystems can often regenerate after significant upheaval, leading to the emergence of new species and ecological arrangements. However, studying these extinctions reveals more than just recovery. It underscores the interconnectedness of life on Earth. The loss of one species can lead to cascading effects throughout an ecosystem, demonstrating that resilience is not just about bouncing back individually, but also maintaining the balance within ecological networks. Understanding these dynamics helps scientists predict how current and future species may respond to ongoing environmental pressures, such as climate change and habitat destruction. By examining these historical episodes, we learn not only about Earth's capacity to recover, but also about the delicate balance of ecosystems. This knowledge encourages a deeper appreciation of biodiversity, reminding us of the importance of conservation efforts today to ensure that our planet continues to thrive, safeguarding the intricate web of life for generations to come. Throughout Earth's history, mass extinctions have dramatically reshaped the planet's biodiversity. Each time life seemed to be wiped out in large swathes, those species that survived faced an environment rich with opportunity. The survivors adapted, diversified, and carved out new ecological niches, leading to evolutionary trajectories that often produce surprising results. After each extinction, whether it was the Permian-Triassic event that eliminated nearly 90% of all species or the Cretaceous-Paleogene event that wiped out the dinosaurs, the remaining species experienced a period of what scientists call evolutionary radiation. This is when a group of organisms rapidly diversifies to fill the vanished ecological roles. For instance, after the extinction of the dinosaurs around 66 million years ago, mammals seized the chance to expand into areas previously dominated by reptiles, leading to the rich variety of mammals we see today. The process of evolution itself thrives on small changes over long times. The survivors, often with unique adaptations that had previously been of little use, found themselves in environments where those characteristics became advantageous. For example, some small fur-like creatures developed traits that allowed them to thrive in diverse habitats, giving rise to the myriad forms of mammals, from tiny shrews to the massive whales we see today. This fascinating cycle of destruction, followed by renewal, teaches us valuable lessons about resilience and adaptability. Evolution is not just gradual, it can be punctuated by significant events that catalyze rapid change. The survivors of past extinctions remind us that even in the wake of devastation, life can recover and flourish, leading to an ever-changing tapestry of biodiversity. The extinction of the dinosaurs, which occurred approximately 66 million years ago, has had a profound impact on human culture and the way we approach scientific inquiry. This cataclysmic event, believed to be caused by a massive asteroid impact, resulted in the disappearance of around 75% of Earth species, including these fascinating reptiles. For scientists, dinosaurs became symbols of evolutionary processes and extinction events, sparking curiosity that led to significant advancements in paleontology. In terms of cultural influence, dinosaurs have captivated the human imagination for generations. They appear in art, literature, and film, drawing awe and wonder from audiences of all ages. Movies like Jurassic Park have not only entertained but also popularized science, inspiring interest in the fields of genetics, paleontology, and evolutionary biology. This cultural fascination has paved the way for the exploration of themes such as survival, adaptation, and the interplay between humans and nature, inviting deeper reflection on our own existence. Moreover, the study of dinosaurs has shown us critical lessons about the Earth's historical climate, changes, and the resilience of life. Understanding the factors that contributed to their extinction allows scientists to draw parallels with current ecological challenges. As we face biodiversity loss and climate change today, the ancient tales of dinosaurs remind us of the delicate balance of ecosystems and the consequences of disruption, fueling scientific inquiry into our role in the planet's future. The dinosaurs' demise has not only enriched human culture, but has also ignited a scientific curiosity that continues to unfold. Our study of these ancient creatures offers insights into evolution, ecology, and our own potential fate as a species. Their legacy lingers in our collective memory, urging us to explore, protect, and appreciate the vibrant tapestry of life on Earth. The age of dinosaurs has sparked a myriad of myths and legends throughout human history, reflecting our fascination with these ancient creatures. Many indigenous cultures have their own interpretations of the fossils they discovered, attributing them to mythical beings or gods. For example, in North America, some Native American tribes believed that large dinosaur bones were the remains of great beasts that roamed the earth long before humans. These bones were often woven into stories that explained the origins of the earth, the creation of mountains, or the last battles of mighty creatures. In Asia, particularly in China, the discovery of large fossilized bones led to intriguing tales. Some legends describe them as the remnants of dragons. The association between dinosaurs and dragons is a common motif, likely because of the similar features they share. The concept of dragons as guardians of wisdom and strength has deep roots in various cultures, further amplifying the dinosaurs' impact on folklore. It seems that for many societies, the colossal figures of the past were not just remnants of history, but living components of their cultural identity. The extinction of dinosaurs has also inspired a wealth of imaginative storytelling. Ancient myths often delve into cataclysmic events, explaining the disappearance of these magnificent creatures. From tales of gods in anger, punishing the earth with massive floods or fiery rains, to narratives about the wrath of nature itself, the mysteries surrounding the dinosaurs' end have provided a rich tapestry for storytelling. These legends often reflect humanity's innate desire to understand and explain the unexplainable, bridging the gap between the ancient past and present concerns about extinction. Moreover, recent times have seen the revival of interest in dinosaurs through popular media, further shaping modern myths. Films, books, and television shows have transformed these creatures into not just subjects of scientific inquiry, but fantastic characters that capture the imagination of new generations. The idea that these creatures could return, or that our interactions with their remnants could somehow bring them back, has bled into contemporary culture, leading to a blend of science and myth that continues to evolve. The story of dinosaurs, from their revered status in ancient myths to their cinematic portrayals today, remains a testament to humanity's fascination with the past and the great questions it raises about life, fate, and extinction. The portrayal of dinosaur extinction in media has greatly influenced how the public understands this monumental event in Earth's history. Films, documentaries, and children's books have often dramatized the causes of extinction, primarily focusing on catastrophic events such as asteroid impacts and volcanic eruptions. This narrative simplifies a complex scientific topic into digestible stories, making it easier for audiences to grasp. The vivid imagery of sudden destruction, Think of a massive asteroid striking the Earth, captures the imagination and creates lasting impressions about how these magnificent creatures met their end. However, these portrayals can lead to misconceptions. While the impact theory, which suggests an asteroid hit the Earth around 66 million years ago, is supported by substantial evidence, it paints a rather singular picture. In reality, the extinction of the dinosaurs was likely the result of a combination of factors. Climate change, geological activity, and sea level fluctuations worked in concert with this cataclysm to create an environment that was inhospitable for many species. Media often overlooks these nuances in favor of a more thrilling narrative, leading to an incomplete understanding among viewers. Moreover, documentaries tend to focus on the dramatic aftermath of the extinction event, often neglecting the rich evolutionary context that preceded it. This can reinforce the notion that dinosaurs were universally dominant until their abrupt end, thereby oversimplifying both their evolution and the intricacies of the ecosystems they inhabited. By concentrating on iconic species like Tyrannosaurus rex, media can inadvertently perpetuate the idea that dinosaurs were a homogeneous group rather than a diverse array of creatures with varied adaptations and survival strategies. As a result, while media representations of dinosaur extinctions have succeeded in igniting interest and curiosity about these prehistoric giants, they have also introduced a range of inaccuracies. Encouraging critical thinking about these portrayals can foster a better public understanding of the complexities involved in the extinction of the dinosaurs, ultimately leading to a more informed view of Earth's ancient history. Promoting an awareness of these subtleties will help nurture a fascination with not only dinosaurs, but also the intricate patterns of life and extinction throughout time. Fossil discoveries serve as a bridge to our planet's distant past, revealing the diverse tapestry of life that once flourished. Each new find holds the potential to answer profound questions about evolution, extinction, and the environmental conditions that shaped the Earth. For scientists, these remnants of ancient organisms not only help to reconstruct past ecosystems, but also provide crucial insights into how life adapts to changing climates and environments. This ongoing exploration fuels a sense of curiosity and excitement, as each fossil can unlock a story waiting to be told. The thrill of finding a fossil is universal, captivating both scientists and the public. When a new dinosaur skeleton emerges from rock or a rare plant imprints surfaces, it sparks imagination and wonder. People are often drawn to the mystery of how these creatures once lived, what they ate, and how they interacted with other species. Museums and educational programs frequently showcase these findings, making science accessible and engaging to a broader audience. Visitors are often left in awe, peering at bones and skeletal models, contemplating their ancient context. Moreover, fossil discoveries can challenge long-held beliefs or assumptions about the history of life on Earth. The unveiling of a new species or a surprising characteristic can turn accepted theories on their head, prompting lively debates within the scientific community. This dynamic nature of paleontology showcases the evolving nature of science itself, where new evidence continually reshapes our understanding and invites fresh perspectives on how life has developed. Additionally, the excitement surrounding fossils often finds its way into popular culture, inspiring films, books, and television shows. These narratives bring paleontology to life for the public, further igniting interest and engagement. As society grapples with questions about our planet's future, the past revealed through fossils offers critical lessons. Each discovery connects us to a history that informs our understanding of biodiversity and the factors that threaten it today. Ultimately, fossil discoveries are not merely remnants from an ancient world. They are narratives that continue to unfold, inviting all of us to participate in the journey of discovery. The transition from the Cretaceous to the Paleogene period, roughly 66 million years ago, marked a significant turning point in Earth's climate and environment. During the Cretaceous period, the planet experienced a warm climate, with high sea levels and lush vegetation thriving in a greenhouse atmosphere. Dinosaurs roamed freely in expansive subtropical habitats, while marine reptiles and diverse marine life flourished in abundant oceans. However, a dramatic event marked the end of this era: the catastrophic impact of a large asteroid in what is now the Yucatan Peninsula in Mexico. This colossal impact released an enormous amount of energy, equivalent to millions of atomic bombs. It created a massive crater and triggered wildfires, tsunamis, and a nuclear winter scenario, where dust, soot, and debris blocked sunlight from reaching the Earth's surface. As a result, temperatures plummeted, dramatically shifting the global climate from the warmth of the Cretaceous to the cooler conditions of the Paleogene. As the dust settled and the immediate aftermath of the impact waned, Earth's climate began to change. Over thousands of years, the planet experienced a gradual cooling trend. This led to significant changes in ecosystems, as many species, particularly those reliant on stable, warm conditions, faced extinction. The lush forests and warm seas gave way to a more temperate climate, allowing for the evolution and diversification of mammals, birds, and flowering plants. This transformative period set the stage for the rise of new life forms in the Paleogene. It marked the end of the age of dinosaurs and heralded a world where mammals began to occupy ecological niches previously held by these magnificent reptiles. This dramatic shift underscores the enduring impact of climatic and environmental changes on the course of life on Earth, a theme that resonates throughout the planet's history. The Paleogene period, stretching from about 66 million to 23 million years ago, brought significant climatic fluctuations that reshaped our planet's environment. This era marks the time following the demise of the dinosaurs and sets the stage for the flourishing of mammals and birds. Across its three subdivisions, Paleocene, Eocene, and Oligocene, climate varied dramatically, influenced by tectonic movements, ocean currents, and evolving vegetation. In the early Paleocene, Earth's climate was considerably warm and stable. Tropical conditions prevailed, allowing lush vegetation to thrive across much of the planet. Regions that today are polar experienced a subtropical environment, contributing to a diverse ecosystem. However, as the Paleocene progressed into the Eocene, the warmth intensified, leading to a peak in global temperatures. It was during this phase that we see the development of expansive forests and the first appearance of modern mammals. Some of the most dramatic changes occurred during the Eocene, especially in its latter stages. There were notable shifts towards cooler temperatures, partially due to the uplift of the Himalayas, which altered wind patterns and ocean currents, paving the way for different climatic regions to emerge. This period also saw the onset of glaciation events, specifically the onset of ice sheets in Antarctica, leading to more pronounced seasonal variations in climate. As the Paleogene came to a close, the climate continued to cool and dry, signaling a transition that would lead to the climatic patterns we recognize today. By the end of the Oligocene, conditions had shifted towards a more temperate climate, with pronounced ice ages on the horizon. These fluctuations were not isolated events, but interconnected dynamics that would eventually shape the evolution of life on Earth as we know it, marking the Paleogene as a crucial chapter in the planet's climatic history. The extinction of the dinosaurs, which occurred about 66 million years ago, marked a significant turning point in Earth's climate history. Following this mass extinction, which many believe was caused by a catastrophic asteroid impact, greenhouse gases began to play a more influential role in shaping the planet's climate patterns. These gases, including carbon dioxide and methane, began to accumulate in the atmosphere, altering the conditions of the Earth's environment. In the aftermath of this extinction event, the drastic reduction in biodiversity created an opportunity for new species to emerge and thrive. As plants and organisms repopulated the Earth, they responded dynamically to the changing conditions caused by increased greenhouse gas concentrations. As more carbon dioxide entered the atmosphere, it led to a greenhouse effect that warmed the planet. This warming opened the door for lush vegetation and diverse ecosystems to flourish, giving rise to what we now know as the Age of Mammals. As the climate continued to warm, it significantly affected global weather patterns. Regions that were once cooler became more temperate, while areas near the equator experienced increased humidity and rainfall. This change prompted shifts in vegetation and habitat distribution, directly influencing the evolution of many species. For instance, the emergence of grassy plains encouraged the evolution of large herbivorous mammals, which in turn impacted predators. Interestingly, the effects of greenhouse gases did not stabilize immediately. Fluctuations continued for millions of years, leading to periods of significant climate change. These shifts remind us of the delicate balance within our planet's climate systems and how interconnected biological and environmental factors are. Understanding these historical patterns provided crucial insights into how greenhouse gases can sculpt climates, which resonates with contemporary conversations about climate change and global warming today. Climatic changes throughout Earth's history have had profound effects on the survival and adaptation of both plants and animals. These shifts in climate, whether they involve warming or cooling, altered habitats, influenced food availability, and reshaped ecosystems. For instance, when the Earth experienced glacial periods, much of the northern hemisphere was covered in ice. Many species adapted to these colder climates, developing thicker fur or changing their migratory patterns to ensure survival. On the flip side, periods of warming, such as during the end of the last ice age, prompted the expansion of forests and grasslands into areas previously dominated by ice. This shift in vegetation opened new niches for various creatures. Animals that thrived in colder environments had to either migrate to cooler areas, adapt to warmer conditions, or face the risk of extinction. Many species evolved tactics to cope with heat, such as behaviors to find shade during the hottest part of the day or developing physiological changes to conserve water. Plants, too, responded to climate changes in remarkable ways. They often had to alter their growing seasons, with some species blooming earlier in response to warmer temperatures. Others evolved deeper root systems to access groundwater in drier periods. In certain cases, rapid genetic adaptations allowed species to thrive in altered environments. The migration of some plant species to higher altitudes or latitudes became necessary as their traditional habitats changed or became inhospitable. This constant interplay between climate and species adaptation is part of an intricate dance of life on Earth. Species that could not adapt quickly enough faced extinction, while others flourished, leading to the complex biodiversity we see today. Whether through gradual evolution or sudden shifts, the resilience of life continues to be a testament to nature's ability to adapt to an ever-changing planet. The extinction of dinosaurs, which occurred roughly 66 million years ago, was a pivotal moment in the history of life on Earth. This cataclysmic event cleared the ecological stage for a dramatic shift in the evolutionary landscape. By removing such dominant creatures, dinosaurs made way for mammals and other groups to flourish in a variety of niches that had previously been dominated by these ancient reptiles. In the absence of dinosaurs, mammals underwent a remarkable transformation. They diversified rapidly and evolved into new forms, filling roles left vacant by the extinct reptiles. Among these new mammals, certain species began to evolve into apex predators. For instance, during the period known as the Paleogene, creatures like the ancestors of modern carnivores emerged, adapting to hunt and thrive in ecosystems that once supported formidable dinosaurs. Without the competition and predation pressure from these large reptiles, mammals expanded both in size and ecological variety. One of the most notable examples of this evolutionary explosion is the evolution of large predatory mammals, like the ancestors of today's cats and dogs. Over millions of years, these mammals not only adapted to hunting smaller prey, but eventually evolved into larger forms, capable of taking down substantial animals, showcasing the adaptability of life in response to changing environmental conditions. This shift underscores the resilience of evolutionary processes, demonstrating that when one lineage goes extinct, it can create opportunities for others. Ultimately, the removal of dinosaurs allowed mammals to take center stage in the evolutionary narrative. This transition facilitated the rise of fierce new hunters that would come to dominate the food chain, setting the stage for the intricate ecosystems we observe today. The impact of that long-ago extinction is still felt millions of years later, as life continuously adapts and evolves to fill the empty spaces left behind. In the grand tapestry of nature, the emergence of new top predators has often shifted the balance within ecosystems. These apex creatures, unhindered by natural enemies, develop unique strategies that enable them to assert dominance over their habitats. Whether through physical adaptations, hunting techniques, or behavioral traits, each species finds its own way to thrive at the highest levels of the food chain. One especially effective strategy involves the development of superior physical attributes. Larger size, heightened senses, and, in many cases, advanced mobility allow these predators to hunt more efficiently. For example, the great white shark utilizes keen eyesight and an acute sense of smell to detect prey from vast distances. Meanwhile, the muscular build and nimble agility of wolves enable them to employ pack hunting tactics, organizing their efforts to take down larger prey, ensuring a higher success rate during hunts. Additionally, some new top predators exhibit remarkable intelligence and adaptability, enhancing their ability to survive and dominate. Cunning strategies such as ambush, stalking, and the use of tools are evident in species like the orca. Orcas are known to work collaboratively to create waves that topple ice floes, allowing them access to seals resting atop. This combination of teamwork and intelligent planning places them firmly at the top of the marine food chain. Lastly, the emergence of top predators often leads to a phenomenon known as trophic cascades. When new dominants enter an ecosystem, they can reduce the population of herbivores below them, allowing plant life to flourish. This balance leads to healthier ecosystems with vibrant diversity and stability. The intricate relationships between species illustrate the remarkable strategies that allow new top predators to not only survive but thrive in their environments, shaping the ecological narratives that unfold in our natural world. In the vast tapestry of Earth's history, the evolution of predator-prey relationships has taken many twists and turns. During the era of dinosaurs, which lasted for around 160 million years, formidable predators like Tyrannosaurus rex dominated the landscape. However, with their extinction about 66 million years ago, a significant shift occurred. This event opened the door for smaller mammals and birds to emerge as key players in these relationships, ushering in a new chapter in evolutionary history. In the absence of giant predators, smaller mammals began to diversify and adapt to the ecological niches left behind. Without the burden of constant predation from enormous dinosaurs, these creatures could develop unique adaptations. For instance, some began to grow in size for better defense, while others became more agile or developed keen senses to evade predators. The presence of these new mammals also meant that various smaller predators arose, each adapting to hunt the myriad of herbivorous species that now flourished. As ecosystems evolved, so did the complex strategies within predator-prey dynamics. The rise of smaller carnivores, such as weasels and felids, meant that their prey had to adapt quickly to survive. This led to an arms race of sorts, where prey species developed speed, camouflage, or defensive mechanisms, while predators enhanced their hunting skills, strategies, and social structures. It was a dance of evolution that was tightly intertwined with survival. This intricate web of relationships showcases the resilience of nature. It highlights how life on Earth is not static, but rather a dynamic interaction between various species and their environments. The extinction of large dinosaurs not only paved the way for mammals, but also set the stage for the diverse predator-prey relationships we observe today, continuously evolving and adapting to the ever-changing world. Saber-toothed mammals, also known as saber-toothed cats, were part of a diverse group of predators that roamed the Earth millions of years ago. One of the most famous members of this group is Smilodon, which lived during the Pleistocene epoch, around 2.5 million to 10,000 years ago. These fascinating creatures developed their iconic, long, curved canine teeth to grasp and hold onto struggling prey. While often perceived as cats, they belong to a different lineage from modern felines, indicating an intriguing evolutionary divergence. The evolutionary path of saber-toothed mammals reflects a response to environmental changes and prey availability. As the Earth entered cooler climates, most larger herbivores, like mammoths and giant ground sloths, evolved. In turn, saber-toothed predators adapted to hunt these massive creatures. Their robust build and powerful forelimbs equipped them for subduing large prey, showcasing how evolution finely tunes species to fit specific ecological niches. In contrast, other dominant predators during this period included the dire wolves and short-faced bears. These creatures followed different evolutionary paths, adapting to their surroundings in unique ways. Dire wolves, for instance, evolved to thrive in packs, which allowed them to hunt successfully in a variety of environments. Meanwhile, short-faced bears, larger than today's bears, developed adaptations for both scavenging and predation, effectively competing with saber-toothed cats. Together, these evolutionary journeys illustrate the dynamic nature of ecosystems. While saber-toothed mammals specialized in unique adaptations for hunting, other predators blended strategies that emphasize social behavior or sheer size. Ultimately, the demise of many of these formidable predators around 10,000 years ago, linked to climate change and human activity, reinforces the idea that evolution continuously shapes the tapestry of life on Earth, with species rising and falling based on their ability to adapt to ever-changing environments. The extinction event that marked the end of the dinosaurs approximately 66 million years ago created a profound shift in Earth's ecosystems. This cataclysmic event, believed to be caused by a massive asteroid impact, led to the extinction of nearly 75% of all species, deeply affecting both terrestrial and marine life. However, the marine realm experienced a remarkable rebound in the aftermath of this tragedy. As the dust settled and conditions stabilized, a new chapter in marine evolution began. The extinction of dominant species, particularly large reptiles like mosasaurs and ichthyosaurs, opened ecological niches that were ripe for occupation. With these formidable predators gone, smaller organisms had the opportunity to thrive and diversify. For instance, bony fish began to flourish, developing into a plethora of new species that adapted to various environments in the oceans. Likewise, the absence of these top predators allowed for the proliferation of other marine life forms, including the ancestors of modern mammals, which began to adapt and explore new evolutionary pathways. Over millions of years, the shallow coastal ecosystems that rebounded were home to rich, diverse communities. Coral reefs, which had been disrupted during the extinction event, slowly re-established themselves. These reefs not only served as vital habitats for countless marine species, but also became a cornerstone of marine biodiversity. Additionally, the rise of grazing organisms, like mollusks and sea urchins, helped stabilize the ecosystem by feeding on algae and sea flora, allowing marine habitats to flourish once again. This recovery ultimately paved the way for the emergence of complex and diverse marine ecosystems that we see today. From the first marine mammals that began appearing to the astonishing variety of fish and invertebrate species, the oceans transformed remarkably over a course of millions of years. The resilience of marine life following the extinction event not only showcases the power of evolutionary processes, but also reminds us of the intricate connections within our planet's ecosystems, which continue to shape the life we observe today. As the Earth's climate shifts, aquatic life faces a myriad of challenges in adapting to new ocean conditions. One significant issue is the increase in water temperature. Fish and marine mammals, like other animals, rely on specific temperature ranges to thrive. Warmer waters can alter their reproduction rates, migration patterns, and even their overall health. Species that cannot adapt quickly enough may find themselves struggling to survive in their traditional habitats, leading to changes in the biodiversity of marine ecosystems. Another pressing challenge is ocean acidification. As carbon dioxide levels rise in the atmosphere, a portion of this gas is absorbed by the oceans, leading to more acidic waters. This process can have dire consequences for calcifying organisms such as corals, shellfish, and some plankton. These creatures depend on calcium carbonate to create their shells and structures. With increased acidity, it becomes harder for them to build and maintain these essential features, jeopardizing entire ecosystems that rely on these organisms for habitat and food. Additionally, the alteration of ocean currents and salinity levels due to climate change affects nutrient distribution, which is crucial for marine food webs. Certain species rely on specific currents for their migration, feeding, and reproductive behaviors. Disruptions in these patterns can result in mismatches between predator and prey, impacting survival rates and ecosystem balance. As these forces continue to change, aquatic life must not only adapt to new physical environments, but also navigate the shifting relationships within their ecosystems. Despite these significant obstacles, resilience exists within many species. Some fish are already exhibiting rapid changes in behavior and physiology to cope with increasing temperatures. Researchers are studying these adaptations to understand how certain species may thrive in a warming world. The ongoing shift in ocean conditions presents a profound challenge, but it also underlines the remarkable adaptability of life and the delicate balance that sustains marine ecosystems. Coral reefs are often referred to as the rainforests of the sea, and their evolution is a captivating story that unfolds over millions of years. These vibrant ecosystems began to take shape long before they became the colorful underwater gardens we see today. The evolution of coral reefs can be traced back to the Triassic period, roughly 240 million years ago. During this era, the Earth underwent significant changes, including shifts in climate and sea levels, which set the stage for the emergence of the first reef-building corals. As time progressed, different species of corals evolved to thrive in the warm, shallow waters of tropical and subtropical regions. The symbiotic relationship between corals and tiny algae, known as zooxanthellae, played a critical role in this evolution. These algae live within the coral tissues and perform photosynthesis, converting sunlight into energy that benefits both themselves and the coral. This mutualistic relationship allowed corals to grow rapidly and build extensive structures, transforming the ocean floor and creating habitats for countless marine organisms. Throughout the ages, coral reefs faced numerous challenges, including climate fluctuations, changes in ocean chemistry, and mass extinction events. The most dramatic changes to these ecosystems occurred around 65 million years ago, during the event that wiped out the dinosaurs. Following this extinction, coral reefs began a slow recovery and continued to diversify, leading to the complex ecosystems we recognize today. They became vital habitats, supporting a staggering array of marine life, including fish, mollusks, and various invertebrates. Today, coral reefs remain essential not just for biodiversity, but also for human well-being. They act as natural barriers protecting coastlines from storms and erosion, and they support fisheries that many communities depend on. However, despite their resilience and ancient origins, these ecosystems are currently threatened by climate change, pollution, and overfishing. Understanding the evolution of coral reefs enriches our appreciation for their beauty and underscores the importance of conserving these incredible marine environments. In the wake of the mass extinction that wiped out the dinosaurs about 66 million years ago, the oceans underwent significant transformations. As the world changed, so too did the marine environment, prompting marine mammals to adapt in remarkable ways. The disappearance of many terrestrial predators allowed a variety of ecosystems to flourish, which created new niches in marine habitats for mammals to exploit. One of the most compelling adaptations involved shifts in diet and feeding strategies. Early marine mammals, such as proto-whales and seals, developed specialized teeth and even the ability to echolocate. This adaptation allowed them to thrive in the vast and diverse ocean ecosystems that emerged. For instance, baleen whales evolved filtering mechanisms to consume tiny creatures like krill, while toothed whales honed their hunting skills to pursue larger prey. These changes significantly increased their chances of survival in a dynamic environment. The physical adaptations of marine mammals were equally remarkable. Bodies became streamlined, enabling faster and more efficient swimming. Some species, like dolphins, evolved a dome-shaped skull, which housed advanced sensory organs for improved navigation and communication in the dark, deep waters. Additionally, the development of blubber provided insulation against colder temperatures, allowing these animals to inhabit a variety of oceanic climates, from tropical to polar regions. Behavioral adaptations also played a critical role in their survival. Many marine mammals became social, forming strong bonds within pods or groups. This social structure offered increased protection against predators and improved hunting efficiency. These adaptations not only allowed marine mammals to thrive in an ever-changing ocean, but also paved the way for some of the most intelligent and complex behaviors seen in the animal kingdom today, exemplifying the extraordinary resilience of life on our planet. The extinction of the dinosaurs about 65 million years ago was a watershed moment in Earth's history. This cataclysm, believed to be triggered by a massive asteroid impact, sparked a dramatic shift in the planet's ecosystems. In the wake of this devastation, life faced an unprecedented opportunity for recovery and evolution. This period marked the beginning of what we now call the Cenozoic era, a time when mammals began to flourish and diversify, leading to the rich tapestry of life we see today. The recovery of biodiversity after the dinosaurs' extinction happened in phases, reflecting how ecosystems can rebuild and adapt following catastrophic events. Initially, the immediate aftermath saw a world largely dominated by small mammals, birds, and various plants that were able to thrive in the new conditions. Over millions of years, these species evolved, filled various ecological niches, and diversified into countless new forms. Remarkably, many of the modern mammalian orders developed during this time, indicating not only resilience, but also the ability of life to adapt to new environments with changing circumstances. Understanding this historical recovery sheds light on the current biodiversity crisis we face, primarily due to human activities such as habitat destruction, pollution, and climate change. The earlier extinction and subsequent recovery illustrate that while ecosystems can rebound, the process is neither quick nor guaranteed. Each extinction event narrows the genetic pool and interrupts ecological processes, making recovery increasingly difficult. The slower rate of recovery after the last mass extinction compared to earlier recoveries underscores the erosion of species and habitats that may never return to their former states. Moreover, the history of biodiversity recovery emphasizes the interconnectedness of life. The roles species play within ecosystems mean that the loss of one species can have cascading effects on many others. As we navigate a world facing unprecedented environmental changes, the lessons of the past remind us of the importance of conservation and holistic environmental stewardship. Protecting the complex web of life is essential, not just for preserving individual species, but for ensuring the stability and resilience of ecosystems as a whole. Throughout Earth's history, climate change has been a constant companion, shaping the environment and influencing life on a global scale. When we look at past climate changes, such as the ice ages or the warming periods that followed, we can draw significant parallels to the present day. For instance, both past and current changes in climate tend to be driven by a variety of factors, including volcanic activity, solar radiation fluctuations, and shifts in ocean currents. However, what sets today apart is the substantial impact of human activity. The current climate crisis is largely fueled by the accumulation of greenhouse gases in the atmosphere, primarily from burning fossil fuels and deforestation. In the past, natural processes like variations in the Earth's orbit, often referred to as Milankovitch cycles, played central roles in climate shifts. While these natural cycles still exist, the speed and scale of today's changes vastly surpass anything observed historically. This rapid alteration in climate is unprecedented and poses risks to ecosystems and human societies alike. Examining the past teaches us about resilience and adaptation. During historical climate shifts, species either evolved to survive changing conditions or faced extinction. In contemporary times, the challenges remain the same, yet our tools for addressing them have evolved. We have advanced scientific understanding and technology that allow us to not only monitor climate change, but also develop strategies to mitigate its effects, such as renewable energy sources and conservation initiatives. Ultimately, drawing parallels between past and present climate changes reveals a continuous narrative of challenge and adaptation. Understanding these cycles and the lessons they offer is crucial as we navigate the complexities of the changing climate today. As we reflect on the Earth's climate history, it becomes clear that while the mechanisms may vary, the need for action and adaptation remains as pressing as ever. Studying life that emerged after the age of dinosaurs provides scientists with invaluable insights into how ecosystems respond to significant changes. The extinction event that wiped out the dinosaurs around 66 million years ago paved the way for mammals and birds to flourish, leading to a rich tapestry of life that would evolve into the diverse ecosystems we see today. By understanding this transformative period, we can gain a clearer picture of how life adapts and evolves in the face of catastrophic events. During the post-dinosaur era, the Earth underwent dramatic shifts in climate, geography, and biodiversity. These changes sculpted new ecosystems, providing a natural laboratory for scientists. For instance, examining fossil records reveals how species adapted to new conditions, such as varying temperatures and resources, which is particularly relevant today as we face climate change. Insight into these adaptations can inform our predictions of how current species might respond to ongoing environmental pressures. Additionally, the recovery patterns observed in post-dinosaur life illustrate resilience. Ecosystems that had previously been devastated began to rebound, albeit in different forms. This resilience is critical as we look at how human activities, such as deforestation and pollution, disrupt ecosystems. By drawing parallels from history, scientists can better understand which species are likely to thrive or decline in our changing world, and which ecosystems may be more vulnerable. Finally, the post-dinosaur era showcases the complex interplay between species and their environments. The extinction of dominant species opened niches for others, leading to increased biodiversity. By studying these dynamics, we can devise strategies to protect endangered species and restore ecosystems today. The past not only teaches us about resilience and adaptation, but also highlights our responsibility to nurture and sustain the ecological balance on Earth. The lessons from post-dinosaur life serve as both a warning and a beacon of hope for the future. The study of past extinction events reveals vital lessons about resilience and the delicate interconnectedness of ecosystems. Throughout Earth's history, various mass extinctions have occurred, each providing insights into how life responds to dramatic changes in the environment. For instance, the Permian-Triassic extinction, known as the Great Dying, wiped out nearly 90% of all species. Understanding the causes of such large-scale losses, including volcanic eruptions and climate shifts, teaches us about the vulnerability of life to rapid environmental changes. One of the most critical lessons is the importance of biological diversity. Ecosystems with a wide variety of species exhibit greater resilience when facing disturbances. This diversity acts like a safety net, allowing some species to survive changes that might wipe out others. Human activities, such as habitat destruction, pollution, and climate change, can diminish this diversity, putting entire ecosystems at risk. Preserving a range of species is not just about saving individual animals or plants. It is essential for maintaining the health of our planet and its ability to adapt to future challenges. Another key takeaway involves the interconnectedness of species. The extinction of one species can lead to a domino effect, disrupting food webs and altering habitats. For example, when the passenger pigeon became extinct, it not only affected the species that relied on it for food, but also influenced the flora it helped to disperse. Protecting biodiversity means safeguarding the intricate relationships between species, ensuring that ecosystems remain balanced and functional. Finally, the lessons drawn from past extinctions highlight the urgency of taking proactive measures today. Climate change poses a significant threat to current biodiversity, much like the past phenomena that triggered mass extinctions. By studying historical events and recognizing the patterns that led to previous losses, we can better understand our role in maintaining the Earth's biodiversity. Ultimately, fostering a deeper appreciation of our natural world is crucial, and this understanding will empower our efforts to protect the diverse life forms that share our planet. Catastrophic events have played a significant role in shaping the course of evolution on Earth. These events, which can range from massive volcanic eruptions to asteroid impacts, create dramatic changes in the environment. They can alter habitats, disrupt ecosystems, and lead to the extinction of numerous species. This sudden upheaval often clears the way for new species to emerge, as niches open up that were previously filled by dominant species that are now gone. One famous example of this is the extinction event that occurred about 66 million years ago. The impact of a large asteroid led to the demise of a significant portion of life on Earth, including the dinosaurs. This event, while devastating, provided an opportunity for mammals to diversify and evolve into the dominant group of animals on the planet. From the ashes of extinction emerged a wealth of biodiversity, showcasing how life can rebound and adapt in the face of catastrophe. Additionally, these catastrophic events can accelerate evolutionary processes such as natural selection. When the environment changes suddenly, organisms that possess traits suitable for the new conditions are more likely to survive and reproduce. This can lead to rapid evolutionary changes, sometimes called adaptive radiation. Species that might have remained relatively stable for millions of years can undergo significant transformations in response to new challenges and opportunities. While catastrophic events can cause immense loss and suffering, they also play a vital role in the tapestry of life. They remind us of the resilience of nature and the ongoing dance of extinction and evolution, a process that continues to unfold over millions of years, shaping the diverse life we see on Earth today. The history of life on Earth is marked by periods of mass extinction that dramatically reshaped ecosystems and allowed for the emergence of new species. One of the most notable examples is the end of the dinosaurs around 66 million years ago. This event, known as the Cretaceous-Paleogene extinction, wiped out approximately 75% of all species. Following this upheaval, mammals, which had previously been small and inconspicuous, began to proliferate and diversify. This led to the rise of mammals into the dominant land animals we see today. Scientists have observed that mass extinction events often create a blank slate for life. With dominant species gone, ecological niches become available, allowing surviving species to adapt and evolve. This phenomenon is known as adaptive radiation. For instance, after the dinosaur extinction, mammals rapidly expanded into various forms, including whales, elephants, and primates. These groups evolved traits suited to their new environments, showcasing the potential for rapid evolutionary change in the aftermath of catastrophic events. Research analyzing the fossil record supports this correlation between extinction and innovation. Paleontologists note that the time immediately following a mass extinction typically sees a spike in the appearance of new species. In some cases, this innovative burst can lead to the emergence of entirely new groups of organisms, like what happened with the ancestors of modern birds, mammals, and even flowering plants, all of which rose to prominence after significant extinction events. The evidence for a link between mass extinctions and subsequent bursts of evolutionary innovation is found in both the fossil record and the patterns of species diversification that occur in the wake of these dramatic events. Ultimately, while mass extinctions are devastating, they paradoxically can serve as powerful catalysts for the evolution of life, demonstrating nature's remarkable resilience and adaptability. The phrase "survival of the fittest," often associated with Charles Darwin, finds special significance in the aftermath of mass extinctions. Following such cataclysmic events, the landscape of life on Earth can drastically change, creating a blank slate for evolutionary processes. Species that survive must adapt to new environments, habits, and ecological niches. This means that adaptability becomes a critical component of survival in these new conditions. In a post-extinction world, the organisms that thrive are often those that exhibit flexibility in their biology and behavior. For example, after the extinction of the dinosaurs, it was the mammals that adapted in numerous ways, leading to a diversification that we observe today. The extinction created opportunities for mammals to occupy roles that were previously dominated by the reptiles. Similarly, plants and smaller organisms capable of rapid reproduction and resilience were crucial in reshaping ecosystems. Moreover, post-extinction scenarios highlight the importance of genetic variation within species. A population that has a diverse genetic makeup stands a higher chance of having individuals that can adapt to sudden environmental changes. This diversity acts like a reservoir of traits that may prove beneficial as conditions fluctuate. A single mutation in a surviving species can lead to adaptations that help it to thrive in a changed landscape, which illustrates the dynamic nature of evolution. Ultimately, survival of the fittest in these contexts emphasizes not a strict competition, but rather the power of opportunity and adaptability. In the aftermath of extinction, those who can best navigate the new environment emerge not just as survivors, but as the architects of future ecosystems. This cycle of life and death is a testament to the resilience of nature and highlights the intricate web of connections that sustains biodiversity on our planet. Throughout Earth's history, catastrophic events have played pivotal roles in shaping both the geology and ecology of our planet. From massive volcanic eruptions to sudden asteroid impacts, these events have dramatically shifted the trajectory of life and the physical landscape. For instance, the most well-known of these events is the asteroid impact that occurred around 66 million years ago, leading to the extinction of the dinosaurs. This catastrophic moment opened up ecological niches, allowing for the rise of mammals and eventually humans. Geological formations, too, have been shaped by these catastrophic events. For example, the intense pressures and heat from volcanic eruptions can transform surrounding rock into entirely new structures. The resulting lava flows and ash deposits create new landforms, which provide unique habitats for various species. Similarly, earthquakes can reshape coastlines and mountain ranges, leaving behind evidence of the dynamic processes that have sculpted our planet over millions of years. After such catastrophes, ecosystems often undergo significant changes. In the wake of mass extinctions, new species evolve to fill the gaps left by their predecessors. The resilience of life demonstrates an incredible ability to adapt. Following the impact that wiped out the dinosaurs, small mammals diversified and evolved into the various forms we see today. In many ways, these catastrophic events act as a reset button, encouraging evolution and the emergence of new biodiversity. Moreover, the geological history recorded in sedimentary layers reveals how these catastrophes have impacted climate and environment. Changes in volcanic activity can lead to periods of warming or cooling, influencing the evolutionary pathways of life on Earth. By studying these past events, scientists gain valuable insight into how our planet responds to dramatic shifts, helping us understand ongoing changes in our current climate. Recognizing the connections between catastrophes and Earth's evolution offers a deeper appreciation for the delicate balance of life and the forces that shape our world. In recent years, paleontology has unveiled a number of fascinating discoveries that broaden our understanding of life following the age of the dinosaurs. One of the most exciting findings involves the incredible diversity of mammals that emerged after the dinosaurs' extinction. The discovery of early mammal fossils, such as those belonging to the group known as Plesiadapiforms, has revealed that mammals quickly diversified into many forms during the Paleocene epoch, adapting to a variety of ecological niches. These mammals were predecessors of modern primates, and their evolutionary journey is reshaping our understanding of how mammals came to dominate the Earth. Another remarkable finding focuses on the remarkable adaptations of birds, which are the only surviving lineage of theropod dinosaurs. Recent fossil discoveries have showcased a variety of bird species that flourished during the Cenozoic era. For example, fossils of giant flightless birds, such as the elephant bird from Madagascar, have shed light on the scale and diversity of avian life after the dinosaurs. These birds not only highlight evolutionary adaptations for survival, but also provide insights into the ecosystems of the time, revealing a world profoundly different yet interconnected with what we observe today. Paleontologists have also made strides in uncovering the world of reptiles that thrived after the dinosaurs. Discoveries of ancient crocodilians that have been identified as active predators, some even capable of taking to land, show the remarkable adaptability of reptilian life. The fossil record now presents evidence of many diverse forms, including the large marine reptiles known as mosasaurs. These creatures dominated aquatic ecosystems and were significant players in the ecological landscape of the post-dinosaur world. Furthermore, the role of climate change in shaping these ecosystems is becoming increasingly clear. Studies of sediment records and fossil remains have shown how shifting climates and environments drove evolutionary pressures that led to the rise of new species in the wake of dinosaur extinction. By piecing together these clues, scientists continue to explore the intricate tapestry of life that followed the age of dinosaurs, uncovering a breathtaking narrative of resilience and adaptation that still resonates in the world around us today. The discovery of new fossil sites has profoundly transformed our understanding of life after the age of dinosaurs. Paleontologists have unearthed an astonishing array of fossils that reveal rich ecosystems flourishing after the mass extinction event that wiped out these majestic creatures approximately 66 million years ago. Far from being a wasteland, this period, known as the Paleogene, was a time of significant evolutionary experimentation and diversification. At these new sites, scientists have found an abundance of mammals, birds, and even primitive primates, indicating that dinosaurs were not the only dominant life forms during the Mesozoic era. The evidence suggests that mammals rapidly evolved in size and complexity after the extinction of the dinosaurs. For example, previously dominant groups such as large reptiles gave way to nimble mammals that began filling ecological niches left vacant. From tiny insectivores to colossal creatures like the giant elephant-like mammals that would eventually roam the Earth, these finds have painted a picture of resilience and adaptability in nature. Furthermore, the discovery of vibrant plant fossils has altered our perception of post-dinosaur ecosystems. Fossils of flowering plants from this period highlight a significant shift in vegetative landscapes, contributing to a diverse food web that supported the evolving animal life. The fossilized remains of interactions, such as predation and competition among species, offer clues into the intricate relationships that emerged in this rebounding world. Each new fossil site acts as a window into the past, revealing the post-dinosaur world as a dynamic and diverse habitat. The findings continue to enlighten our understanding of evolution and biodiversity, showing how life on Earth not only persisted but also thrived, paving the way for the myriad forms we see today. The exploration of these ancient sites remains vital in unraveling the complex tapestry of life and evolution following one of the most significant events in Earth's history. Amateur fossil hunters play a significant and often undervalued role in the study of prehistoric eras. These passionate individuals contribute to paleontology by discovering and collecting fossils that may otherwise remain hidden beneath the Earth. Their enthusiasm and dedication lead to exciting discoveries, sometimes unearthing species that have never been documented before. Each find provides valuable insights into the history of life on our planet and sheds light on evolutionary processes. One of the remarkable aspects of amateur fossil hunting is the sheer volume of discoveries made outside professional excavations. Fossils of all kinds, from tiny invertebrates to large dinosaurs, have been found in quarries, riverbanks, and in fields. Oftentimes, these findings complement formal scientific research, broadening our understanding of specific periods and environments. When amateurs document their discoveries with proper care, they create a treasure trove of data for scientists to analyze and study further. Collaboration between amateur enthusiasts and professional paleontologists can be especially fruitful. By sharing their finds and expertise, amateur hunters contribute to a larger body of research. Many professional institutions encourage this partnership, providing resources and guidance to help amateurs ensure that their discoveries are scientifically useful. This synthesis of amateur enthusiasm and scientific rigor helps to bridge the gap between casual interest and serious research. As we continue to explore our planet's ancient past, the contribution of amateur fossil hunters remains invaluable. Their discoveries enhance our understanding of biodiversity, extinct species, and ancient ecosystems. In this age where time spans can be incomprehensibly long, every fossil tells a story, and every story is a piece of the intricate puzzle of life on Earth. Interdisciplinary approaches play a crucial role in enhancing our understanding of historical geology and paleobiology by integrating knowledge from various scientific fields. This collaboration allows researchers to reconstruct past environments and life forms with greater accuracy and depth. For instance, by merging principles from biology, geology, chemistry, and even physics, scientists can gain insights into ancient ecosystems, the processes that shape them, and the life forms that inhabited them. In paleobiology, the study of ancient life, the incorporation of genetic analysis and modern biology has illuminated how species evolved over millions of years. Paleontologists can now extract DNA from ancient remains, providing a window into the genetic diversity and lineage of extinct species. This genetic information, when combined with the fossil record, helps establish evolutionary relationships, shedding light on how organisms adapted to their environments. The result is a richer understanding of life's history on Earth. On the geological side, advances in technology and method have allowed geologists to assess rock formations and sediment layers more comprehensively. Techniques such as radiometric dating, which tells us the age of rocks, are now enhanced by data from climate science and environmental studies. This fusion of knowledge allows scientists to interpret not just when geological events occurred, but also the ecological conditions that existed at those times. The interplay of these disciplines is essential for addressing broader questions about Earth's history and the impact of climate change, mass extinctions, and the evolution of life. By combining various perspectives and methodologies, researchers can paint a more complete picture of the past, helping us understand present-day biodiversity and informing future conservation efforts. Such interdisciplinary collaboration truly enriches our exploration of Earth's geological and biological history, revealing the intricate tapestry of life and its environmental context. The early Paleogene period, which followed the mass extinction event that wiped out the dinosaurs about 66 million years ago, is marked by profound changes in Earth's ecosystems. Fossil records serve as one of the most convincing pieces of evidence highlighting these shifts. Within this period, which spans from about 66 to 33 million years ago, paleontologists have unearthed a rich diversity of plant and animal fossils across various continents. One striking feature of this time was the rapid evolution of mammals. After the extinction event, mammals began to diversify significantly, occupying ecological niches that were previously dominated by dinosaurs. Fossils reveal the emergence of a variety of mammalian forms, from small insectivores to larger herbivores. This diversification indicates a shift towards warmer climates, enabling the growth of lush forests that supported new life forms, including early primates. In addition to mammals, variations in plant life are equally telling. palynological evidence, which involves the study of pollen grains, illustrates that flowering plants became increasingly more prevalent during this period. The appearance of tropical and subtropical forests allowed for rich biodiversity, reflecting warmer temperatures, shifting weather patterns, and increased levels of carbon dioxide in the atmosphere. Such transformations contributed to the establishment of ecosystems that laid the groundwork for the extensive environments we recognize today. Moreover, marine ecosystems experienced significant changes. Evidence from sediment cores shows a rise in ocean temperatures, affecting marine life and leading to shifts in species distribution. Coral reefs thrived, offering habitats to diverse fish species, while larger marine mammals began to appear. These interconnected shifts in terrestrial and marine ecosystems during the early Paleogene underscore the dynamic nature of life on Earth following one of its most significant extinction events. The Earth's tilt and orbit play fundamental roles in shaping our climate over long periods, especially following the age of the dinosaurs. These factors are part of a complex system called Milankovitch cycles, which influence the distribution of solar energy on our planet. The Earth's axial tilt, or obliquity, varies over roughly 40,000 years. This tilt affects seasonal contrasts. During periods of a greater tilt, summers become warmer and winters colder, leading to significant changes in climate patterns over time. Additionally, the Earth follows an elliptical orbit around the Sun that changes shape over cycles of about 100,000 years. This orbit influences the distance from the Sun, thereby impacting the intensity of sunlight the Earth receives. A more circular orbit generally means less variation in the climate from season to season, while a more elliptical orbit causes greater fluctuations in temperature, possibly leading to colder winters and hotter summers. These changes have profound effects on global climate. For instance, after the dinosaurs went extinct 66 million years ago, these cyclical shifts allowed periods of significant cooling and warming. Ice ages emerged as ice sheets formed during periods of increased tilt and a more elliptical orbit. As these ice sheets expanded and contracted, they created a host of environmental changes, reshaping ecosystems and altering species' survival and migration patterns. In the millennia that followed, these climate shifts contributed to the rise of diverse ecosystems, eventually paving the way for mammals and later humans. Understanding how the tilt and orbit of the Earth influences climate helps us appreciate the delicate balance of our environment and the dynamic history of our planet's climate. The legacy of these geological phenomena is felt even today, reminding us that the cycles of nature continue to shape our world. Weather patterns and storms have played a significant role in shaping the course of evolution on our planet. Over millions of years, the conditions of Earth's atmosphere have fluctuated, influencing not only the climate, but also the habitats where various species thrived. For example, significant weather events can act as catalysts for dramatic changes in ecosystems, often leading to the rise or fall of particular species. One notable impact of storms and shifting weather patterns is the way they can physically alter landscapes. Hurricanes, earthquakes, and even droughts can reshape terrain, create barriers for migration, or wipe out entire populations. Following such disturbances, the process of natural selection takes center stage as species adapt to the new conditions or face extinction. Adaptations can range from developing stronger physical traits to evolving new behaviors that enhance survival in changing environments. Climate change plays a pivotal role as well. As temperatures fluctuate, they directly affect weather patterns, leading to droughts in some areas and floods in others. These changes can shift the availability of resources, such as food and water, thereby influencing species' behaviors and reproductive strategies. For example, species that can migrate or adapt quickly to new habitats may flourish, while those that cannot may dramatically decline. Ultimately, major weather phenomena serve as constant reminders of the ever-changing nature of our planet. They underscore the resilience of life and its ability to adapt through evolutionary processes. By examining the relationship between weather patterns and evolutionary developments, we gain deeper insights into how interconnected the biosphere is with the forces of nature that shape it. The glaciations, or ice ages, that Earth experienced over millions of years have sculpted not just our landscapes, but also significantly influenced the evolution of life. As vast sheets of ice advanced and retreated across continents, they altered ecosystems and the habitats where plants and animals thrived. During glacial periods, the Earth's climate became colder and drier, which caused many species to either adapt, migrate, or face extinction. This constant push and pull shaped a diverse array of life forms that had to cope with the changing conditions. One of the most profound effects of glaciation was the effect on sea levels. During ice ages, large amounts of water were trapped in ice sheets, resulting in lower sea levels. This shift exposed vast coastal areas, creating new habitats such as land bridges. The Bering Land Bridge, for example, linked Asia and North America, facilitating the migration of species, including early humans. As the ice melted and sea levels rose again, these habitats transformed, leading to a rich diversity of marine life. The cyclic nature of glaciations also played a role in developing genetic diversity among species. Isolated populations due to glaciers had to adapt to their specific environments, which led to speciation. Over time, as glaciers receded, these populations came into contact again, allowing for genetic exchange. This blending of traits contributed to the complex web of life we see today. In a way, these icy periods can be viewed as natural laboratories of evolution, where survival hinged on adaptability. Furthermore, glaciations impacted the distribution of resources. As ice sheets broke apart, they left behind fertile soils and mineral deposits, which facilitated agriculture and the rise of civilizations. The end of the last major glaciation around 10,000 years ago marked the beginning of significant human advancement. This period led to the domestication of plants and animals, shaping our current landscape of life on Earth. Glaciations were not merely periods of cold, they were pivotal in forging the path of life on our planet, crafting a dynamic interplay of extinction, adaptation, and evolution. The evolution of giant and small species is a fascinating topic that showcases the adaptability of life in response to environmental pressures. This remarkable phenomenon can often be traced back to the availability of resources, ecological niches, and the specific challenges posed by climate and geography. For instance, in isolated environments like islands, some species may evolve into larger forms due to the absence of predators, a concept known as insular gigantism. The absence of competition allows these species to grow much larger than their mainland relatives. Conversely, certain species become significantly smaller in size, a phenomenon referred to as insular dwarfism. Smaller size can confer advantages in nutrient-scarce environments where conserving energy and resources is essential for survival. This adaptation may be particularly beneficial for species such as rodents or reptiles living in limited habitats where their larger counterparts might struggle to find enough food. In these cases, adapting to a smaller size can enhance their chances of survival. Other factors influencing these size changes include climate fluctuations and the availability of specific habitats. Giant mammals during the ice ages, like the woolly mammoth, thrived in cold climates with abundant vegetation that supported their large size. In contrast, some species may reside in warmer regions where smaller sizes help facilitate heat regulation and mobility. Overall, whether evolving into giants or shrinking into smaller forms, species reflect the intricate dance of evolution under the influence of environmental conditions, resource availability, and competitive dynamics. This ongoing process of adaptation highlights the resilience of life and its capacity to fill various ecological roles across the planet's diverse habitats. After the extinction of the dinosaurs around 66 million years ago, the Earth underwent significant ecological changes. In this new world, mammals began to diversify and expand into ecological niches that were previously dominated by dinosaurs. This period, known as the Paleocene and the subsequent epochs, set the stage for various evolutionary pressures that favored larger body sizes in certain mammalian species. One of the primary factors that encouraged gigantism among these early mammals was the availability of resources. With the decline of dinosaurs, the vegetation flourished, leading to a rich and diverse habitat capable of supporting larger herbivorous animals. These enormous creatures, like the woolly mammoth or the giant ground sloth, had access to abundant food sources, allowing them to grow larger than many of their predecessors. The shape and availability of plant life influenced the size these mammals could achieve. Additionally, larger size often provides certain advantages for survival. Larger animals tend to have fewer natural predators and can defend themselves more effectively. They may also have a greater ability to regulate their body temperature, which is particularly advantageous when facing fluctuations in climate. Larger herbivores can traverse long distances to find food and water, giving them an edge in survival where resources might be sporadic or seasonal. Finally, these evolutionary pressures acted cumulatively, creating a variety of giant mammals across different environments. Gigantism was not uniform, but appeared in various lineages, leading to a fascinating array of enormous mammals adapting to the post-dinosaur world. The interplay of food availability, reduced predation, and thermal advantages created a perfect storm for the emergence of these magnificent large creatures, which continued to flourish until changing climates and new challenges reshaped their fates. The evolution of mammalian species is intricately tied to changes in vegetation, or flora, over millions of years. As Earth's climate shifted, so too did the landscapes, leading to the emergence of diverse environments, from lush forests to open plains. These alterations in flora affected food availability and habitat suitability, which in turn influenced the sizes of mammals that could thrive in these regions. In dense forests, where the vegetation is abundant but competition for resources is fierce, smaller mammals often flourished. These nimble creatures could navigate through thick branches and access food sources that larger animals might overlook. Think of species like tree shrews or rodents, which have adapted their size and shape to exploit niches in the foliage. Their small size allows them to escape predators and find shelter, demonstrating a classic case of evolutionary adaptation driven by the surrounding flora. Conversely, in open grasslands where vegetation is sparse, larger mammalian species began to dominate. These expansive areas favored size, as larger mammals could cover greater distances in search of food. Animals such as elephants and bison thrived in these environments, where their size offered advantages for grazing on tougher grasses and deterring predators. Larger size also allowed these mammals to migrate across vast terrains, seeking new pastures in response to seasonal changes in flora. Ultimately, the changes in flora throughout different geological epochs have been a significant factor in shaping the diversity of mammalian sizes. The interaction between plants and animals remains a fascinating aspect of evolutionary biology, illustrating how life adapts to the ever-changing face of our planet. As we continue to learn about these relationships, we gain deeper insights into the complex tapestry of life that has unfolded over millions of years, guided by the flora that surrounds us. Continental drift and isolation have played a crucial role in the evolution of species on our planet. Over millions of years, the movement of continents has altered the landscapes where organisms live, leading to both opportunities and challenges for the species that inhabit those areas. As continents shifted, land connections were severed, creating situations where populations of the same species were separated. This isolation allowed different groups to evolve independently, often leading to distinct species adapted to their unique environments. One of the most famous examples of this phenomenon is the Galapagos Islands. When Charles Darwin visited these islands in the 1830s, he observed species that were similar yet distinctly different from those on the mainland of South America. The isolation of these islands allowed various species of finches to adapt to the unique conditions and food sources available, resulting in remarkable variations in beak size and shape. Such changes were driven by natural selection, where certain traits offered advantages for survival in specific habitats, demonstrating how isolation can spark rapid evolutionary change. Moreover, continental drift has contributed to the size evolution of species through the concept known as island gigantism. On isolated islands with limited resources and fewer predators, some species can grow larger than their mainland counterparts. One notable instance is the now extinct dwarf elephants that roamed the Mediterranean islands, which were considerably smaller than their relatives on the mainland. Conversely, some island environments led to larger bird species due to the absence of land mammals and specific ecological pressures. Continental drift and the resulting isolation have been instrumental in shaping the diversity and size of species across our planet. By creating opportunities for species to develop in unique environments, these geological processes have resulted in an intricate tapestry of life, showcasing nature's incredible adaptability and resilience. The fascinating stories of evolution remind us of the interconnectedness of all living things and how our world continues to change through geological time. The understanding of extinction has undergone remarkable transformation over the centuries. In the past, extinction was often seen as an isolated event, a fate that befell a few unfortunate species without many implications for the world at large. The dominant view was a simplistic one, where creatures vanished and the world continued on, seemingly unaffected. This notion was challenged during the 18th and 19th centuries when scientists, notably like Georges Cuvier, began to gather evidence of past life forms through fossils, revealing that extinction was a common and natural part of Earth's history. The paradigm shifted dramatically with the advent of evolutionary theory in the 19th century, particularly through the work of Charles Darwin. His insights into natural selection shed light on how species adapt, or fail to adapt, to their changing environments. Extinction, from this perspective, became an essential aspect of the evolutionary process, acting as a driving force for diversification. The extinction of species leads to new niches for others to fill, maintaining the dynamic and ever-evolving tapestry of life on Earth. As we moved into the 20th century, scientists began to see patterns in extinction events, recognizing that large-scale extinctions could have catastrophic global effects. The discovery of the Cretaceous-Paleogene extinction, which wiped out the dinosaurs around 65 million years ago, underscored this idea. It was a turning point that led to a better understanding of mass extinctions and the variety of causes, from abrupt climate changes to asteroid impacts, that can lead to widespread loss of species. Today, our perspective on extinction and survival is more intricate than ever. The role of human activity in accelerating extinction rates is profoundly troubling. Many scientists regard our current era as the sixth mass extinction, primarily driven by habitat destruction, pollution, and climate change. This evolving view emphasizes not only the fragility of life, but also humanity's responsibility in stewardship of the planet. Armed with modern technology and interdisciplinary approaches, scientists continue their work, striving to understand the past and protect the future, emphasizing that understanding extinction is crucial for preserving the plethora of life's diversity. The extinction of entire species invites profound philosophical questions about our place in the universe and our ethical responsibilities toward other forms of life. One key question revolves around the intrinsic value of a species. Are certain species inherently valuable, regardless of their utility to humans? This leads us to consider whether we have an obligation to protect not just those species that benefit us, but also those that have ecological, aesthetic, or cultural significance. Another important question pertains to the implications of extinction for humanity itself. The loss of species can disrupt ecosystems, which are vital for human survival. This raises the question of whether we have a moral duty to prevent extinctions to safeguard our own future. Additionally, it prompts us to examine the balance between human development and conservation. How do we reconcile our need for land, resources, and economic growth with the need to preserve biodiversity? Furthermore, the concept of stewardship emerges. If we see ourselves as caretakers of the planet, what does that mean for our actions? Should we prioritize the needs of our species over others, or do we have a responsibility to maintain the intricate web of life that supports us? The ethical implications of our choices are profound and complex. Lastly, the question of legacy enters the conversation. What should we leave behind for future generations? If species continue to vanish at unprecedented rates, what kind of planet will they inherit? This reflection on legacy forces us to confront not only our environmental impact, but also our interconnectedness with all living things. In considering these questions, we arrive at a deeper understanding of both our responsibilities and our interconnectedness with the natural world. The post-dinosaur era, which began around 66 million years ago, marks a pivotal time in the history of our planet. The extinction of the dinosaurs allowed for a radical transformation in Earth's ecosystems. Suddenly, a wealth of ecological niches became available, leading to an explosion of diversity among mammals, birds, and plants. This period, known as the Cenozoic era, has been crucial for understanding the intricate relationships within ecosystems and the evolutionary processes that shape them. Through studying this era, scientists have gathered invaluable insights into the principles of ecological succession. In areas where enormous organisms once roamed, like the dinosaurs, new species developed to fill the gaps left behind. This progression aids our understanding of how ecosystems recover from disturbances, whether those are natural catastrophes or human impacts today. The re-establishment of diverse habitats highlights the resilience of nature and underscores the importance of conservation efforts in maintaining ecological balance. Additionally, examining fossil records from the post-dinosaur period reveals a wealth of information about climate change and its effect on life. Scientists can trace how different species adapted or failed to adapt to shifts in their environments over millions of years. This knowledge is not just historical, it serves as a critical reference for contemporary challenges, such as climate change. By understanding past adaptations, we can better predict which species might endure the stresses of a warming planet. Ultimately, the study of the post-dinosaur era has greatly enriched our understanding of ecological dynamics. It emphasizes the interconnectedness of life and the delicate balance that sustains ecosystems. As researchers continue to explore this remarkable period, they unravel mysteries that echo into our present, reminding us of the enduring power of adaptation and resilience in the face of change. The research into biodiversity reveals a stark truth. The loss of species impacts not only ecosystems, but also human society. Each species, no matter how small, plays a role in maintaining the balance of its environment. By studying these intricate connections, scientists underscore the ethical responsibility we share in preserving biodiversity. Today, this understanding compels nations, organizations, and individuals to rethink our relationship with the natural world. Ethical considerations in preserving biodiversity hinge upon the recognition that every creature has an intrinsic value. This perspective challenges the traditional view that nature is merely a resource for human consumption. Instead, it promotes a sense of stewardship, where the well-being of the planet is intertwined with our survival and prosperity. As studies highlight the vital ecosystem services provided by diverse species, such as pollination, water purification, and climate regulation, they reinforce the idea that protecting biodiversity is essential not just for wildlife, but for human health and prosperity. Furthermore, these studies inform policies and practices that prioritize conservation efforts. Ethical frameworks have emerged that advocate for sustainable use of resources and the protection of natural habitats. Concepts like ecological justice begin to gain traction, emphasizing that the benefits and burdens of environmental policies should be shared equitably among all communities, particularly those historically affected by environmental degradation. The findings of biodiversity studies enrich our ethical frameworks, pushing us towards actions that honor and protect our planet's diversity. They challenge us to advocate for a future where humans live in harmony with nature, embracing an ethic of care that recognizes our interconnectedness with all life forms. Society's response to these ethical imperatives will shape not only our environment, but also the quality of life for generations to come.